Peter Gärdenfors is a professor of cognitive science at Lund University. He's probably, if you have ever heard about AGM belief revision, he's the G stands for Gärdenfors. And so he's very famous for that. But he has many other distinctions, among which are member on the Nobel Prize Committee for Convex. And so I believe we can all bring him a warm welcome. And he's talking about the juncture meaning semantic space.
Thank you. All right, it's a pleasure to start early, and I hope not too many will be dropping in afterwards here. But anyway, my background, my personal background, I've got my bachelor education in mathematics, computer science, and philosophy. It was a long time since I was an active programmer, but I know what it is at least. And the last 27 years of my life, I've been a professor of cognitive science, and I feel very much like a cognitive scientist. And the last few years, I've become a wannabe linguist. So I dabble a little bit in semantics. The title of my tutorial happens to be the same as the title of my new book that came out last year. And I want to give you a new approach to semantics of natural language. Before I start, I want to give you the really big problem here, what I'm deep down is addressing here. So, if you look at an ordinary child, they grow up, they learn a language, or so they learn several languages. But normally, a teenager who finishes high school understands about 50, 60,000 words of her language. I mean, they don't use it actively, but they understand the meaning of these words. And if you count backwards, that means that they learn 8 to 10 new words. To learn to understand 8 to 10 new words per day. It's almost 1 per hour of waking time. So this learning is extremely quick. And what is more, that you only need to hear one example of a word to pick it up. I mean, sometimes you need more, but very often, I mean, it's shown in the child literature that one exposure to a word is sufficient for a child to have some grasp of its meaning. Maybe not the perfect meaning, but I understand basically that it's a color term or it's a shape term or whatever it is, or a verb. So, the problem I want to do now is that work with is we don't know how this process works. I mean, there are some ideas. And my problem is to give some kind of account, some kind of modeling of this learning process. I mean, it's so efficient. There is no other learning process that is so efficient than this language learning. And all of us go through it. And we don't know very much how it works. And some people, like Chomsky, say that, well, he's not talking about word learning, but some people say that there has to be innate principles. I want to say that there are indeed constraints in our cognition. I mean, we have cognitive structures, constraints on our cognitive processes that speed up this learning process. And what I want to give you is an account of what I think are the constraints here. And instead of using logic and symbolic exposures, I will work with geometrical notions. Vector spaces, convexity, stuff like that. So I have a different way of approaching the representation of semantic knowledge than what is what most people work with. And I'm going to make some propaganda for that approach. And this approach will be, for those of you who work with the semantic web and the web ontologies, this will be very challenging because I'm asking you to reconsider the foundations of your work. So that will be tough for you. Anyway, before I start with my book, let me just give you a very brief summary of the main approaches to representing information. And the first paradigm in cognitive science was what I call symbolism. And that is, I mean, the first idea in cognitive science was that the brain is a computer. The brain is a Turing machine, and it works as with symbols. It's an information processing system, and it has a central processor and a memory units and so on. And for me, the most important part is that this Turing computer runs on some kind of code, symbolic code. And it was thought in the early days of cognitive science that once we crack this code, then we know how the brain works and we can simulate it, we can do the cognitive processing ourselves. But the assumption is that there is some kind of symbolic code, the language of thought. I mean, Jerry Fodor is one who has been proposing this view quite strongly. So that's the beginning. Now, so the Turing machine is a symbol manipulator. And if you do it in logic or in computer science, the basic building blocks of your expressions are the predicates or variables. And then you do all kinds of logical constructions on top of that. I mean, Boolean operators, quantifiers, unification, what have you. My problem is, where do the building blocks come from? Where do we get the predicates? And in particular, where do we get the meaning of the predicates? I mean, yeah, concepts are defined in terms of necessary and sufficient conditions. This is the old Aristotelian idea. How do you define the meaning of a concept? Yeah, you present the necessary and sufficient conditions for applying it. And that's been standard. I mean, there are programming languages like Prolog that is built up more or less on this assumption. So this is a typical definition. A grandmother is a female, and then there is a Y and a Z, so that Y is a child of X and Z is a child of Y. I mean, this is a standard definition of grandmother in terms of necessary sufficient condition. Now, my general problem is, where do the predicates come from? Where do we get the child and the female and how do we get the atoms of the language? The answer is that these are put in by the programmer. Next question is, how do we understand their meaning? I mean, in the symbolic approach, you start from a set of basic predicates, and then you create new concepts using these kinds of operators. But very seldomly do people discuss what is the meaning? How do we get the meaning of the basic predicates? How do we describe the meaning of them? And in particular, how do we learn the meaning of the basic predicates? So for me, this is a problem. This is a limitation of the symbolic approach. Of course, there are people working on it, but in general, this has not been treated very well. And the problem is to have some kind of grounding. And of course, we are agents. We're running around in the world and doing things. And we have to know what is the meaning of the terms in order to do the right action, to interact with the world in the right way. And we need some kind of meaning of the predicate that connects to the world. So these problems of learning the meaning of predicates led cognitive science into a second paradigm, or computer science for that matter, connectionism. And the idea is that, well, maybe the brain is not a Turing computer after all. Maybe the brain works in a different way. And there are these neurons, and the idea was that the neurons work in parallel. They are very simple processes. They take few signals as an input, they do a simple calculation, some kind of summing or multiplying operation, and then they send an output to other neurons. And they do this in parallel, and it's a distributed computation. There is no central processor, there is no particular memory unit, and so on. So this was something that grew up in the 1970s and is still very active as a research area. And so this is the basic metaphor, that you take a neuron and then you build a computational system on the basis of a system of neurons. And of course, there are very many architectures for this. I mean, there are the feed-forward models, and there are recurrent networks and whatnot. There are lots of different architectures in the area. But I don't want to get into the details here. The idea is that this system has a number of receptors. There are no atomic predicates fit in. The receptors come from some kind of external source, a camera, a soundtrack, or whatever, and then these the information fed in by the receptors is organized some way by the neural network. And the meaning of something is then there is no particular neuron that has the task of keeping track of the grandmatter. I mean, there is no grandmatter cell, it's been said. It's a distributed representation, and the representation is built up by the connection of the learning weights in the system. And this system can learn. I mean, the weights between the neurons are changing over time, depending on the successes and failures of the network. One problem is what is represented in the network. And we know that it can classify things correctly after a lot of training, but we have normally difficulties in reading off from the network exactly what it has learned. So that's one problem. And for me, another problem is that learning is in general very slow. You have to train a system, thousands of examples, before it picks up a particular pattern. And this doesn't fit very well with how humans learn languages. So these are my basic criticisms of the two paradigms. So what I want to bring in here is what I call a third paradigm, spatial models. And my idea is that we replace the logic and we replace the neural networks with topological geometrical structures. That's what the kind of mathematics I'm working on. By the way, I will not do very much mathematics here. There will be a few glimpses. But I have the hope that the models I'm specifying here can be computationally implemented. And at the end of my talk, I will give you some examples of what's happening in this area. So conceptual spaces is what I will be talking about. And they are spaces because they have this kind of geometrical structure. Information is organized in spatial structure. Here is a kind of paradigm example. It's known that human color perception comes in 3 dimensions, and that we can organize our color terms and our color judgments along 3 dimensions. One is, one is the hue, going red, blue, green, yellow, and so on. That's a circular dimension. So it's a bit odd. Then we have the intensity, going from gray to more and more intense colors. And the third one is the lightness, brightness, from white to black. These 3 dimensions are not independent. When you come close to the black, I mean, you have fewer discriminations. When you come close to the white, you can make fewer discriminations. So you get this kind of double spindle here. And the point is that what you see here is that we get judgments of similarity. We can say that orange is more similar to red than orange is to blue, because they are closer in space. The spatial organization allows us to talk about similarity. And it's well known that when children learn language, they use similarity quite a lot. And in the symbolic approach, it's very difficult to model these aspects of similarity, how similarity plays a role in learning new concepts. On the spatial model, this comes for free, because this smaller distance means more similar. So we get similarity as part of it. Yeah, that's exactly what I've said now. So now I get to the menu for today. First question is a very philosophical question. What is semantics? I will talk about what should a semantic theory do? I mean, what are the requirements for a semantic theory? Then I introduce my idea, my basic framework, conceptual spaces, and what I call semantic domains. I develop semantics as a meeting of minds. Take these social aspects of semantics seriously, which is not very common in the symbolic approach, not very common in cognitive linguistics either. But I have some kind of model. I've done this together with Massimo Vaglien, a collaborator in Venice. Then, the main semantic, I mean, this is for the linguists, or for computational linguists. I give a cognitive grounding of the different word classes. I give you a theory of why we have word classes, why we don't only have predicates, but why we have different classes of words in languages. Because they have said different semantic roles. And I'll say something about how we can model these semantic roles. I do some of the main word classes. As part of this, as part of understanding the meaning of verbs, I mean, verbs have not been analyzed very formally in most traditions. I have a model of the meaning of verbs, and for that I need a theory of actions. So I have a theory of actions in terms of conceptual spaces, and also a theory of events, because verbs are used to describe events. And I'll say a few words about compositionality of meanings. That would be quite different from how compositionality is treated in the symbolic tradition. And it's not on my list here, but after this I will give two brief examples of applications. One, well, not application, I will say some comments on the relation to the semantic web, and then I will give one example of how we can use these ideas in developing communication systems in robotics. So that's the menu. Please feel free to interrupt me at any point of time. Ask questions, protest, say hooray if you like, and yeah, whatever. Interaction is fun. Okay, let's start. What is semantics? So I put a number of questions here. The first question is the ontological. What actually are meanings? What kind of things are they? I have the semantic question. What is the relation between the speech act, communicative acts, and their meanings? I have the epistemological question. How can we learn the meanings? And for me, that's a very important question. I have the social question. I mean, we are sharing a language. What does it mean to share a language? How can we say that we have the same meanings in language? And yeah, what does this say about communication? So, I mean, I'm bringing out in most of the topics in essence, I think, in this way. And then, of course, language has to be grounded. We are talking about the world, not all the time. We are acting in the world. So I want to have some kind of discussion on how a semantic theory connects the semantics to other cognitive mechanisms, perception and action in particular. So I want this kind of grounding. Okay, these are my questions, so let them do them one by one. And now I just, I do what's happening. Yeah, I do both of them at the same time. In philosophy, semantics has been dominated by truth functional semantics. There are two main answers to the ontological question. One is meanings are out there in the world. The meaning of the word horse is the set of all horses in the world. I mean, that's the extensional definition. And then that's the realistic topic, the idea of meaning. It goes back to Plato, but it's mainly Frege in the modern times that's been developing this. The other alternative is conceptualism. That means that meanings are in the head. Meanings are cognitive constructs. And I'm favoring the conceptualistic approach. Of course, you have nominalism, that words don't have meaning, they are just triggers for behavior. Quine, at some point of time, defended some form of nominalism, but that's not very popular in the current debate. I mean, even in behaviorism, you have something like nominalism. So the tension is between a realistic approach to semantics and a conceptualistic. Truth functional semantics builds on realism. I mean, you can have a cognitive version of truth functional semantics, but most people work in that way. And the traditional Frege-Tarski model is that there is this language, it's an abstract system, it is, in best case, it's a formal language, and then there is the world, and things are true or false about the world, and giving the meaning of an expression is to define its truth conditions. So meanings are truth conditions in the traditional extension of semantics, and that's the starting point for most of analytic philosophy. Now it turned out that, well, we talk about things that are not in the world, we talk about possibilities, the future and the past, things that don't exist, and so on. So we need a little bit more complicated thing than just having a world. So in the 60s, 70s, we got intentional semantics, where you replaced the world with a set of possible worlds, and then you map the meanings onto not one world, but a set. But the idea is still the same. To give the meaning of something is to give its truth conditions. And that gave rise to modal logic. In linguistics, you have Montague grammar and so on. That is based on this kind of intentional semantics. But it's still at the bottom, a realistic semantics. I mean, the possible worlds are thought to exist there, are independent of our minds. The truth conditions are defined independently of our minds. So it's basically a realistic. Then in the 80s, we got well, let's see now, cognitive semantics. And that builds on conceptualism. And there are people like Lannacker, Talmy, Lakoff, Herskovits, and so on that started this tradition. And now the idea is that, well, we have the language in our head, and we have the meanings in our head. And the semantics is a mapping between our cognitive representations of language and our cognitive representations of the world. And the real world comes in later when we're using our meanings to do things in the world. So meaning in this sense, I'm making a caricature here, is independent of the world. It's a conceptual structure. And learning a language is learning the connection between words and their cognitive representations. Cognitive semantics has been focusing on single words, not so much on sentences. While in the truth functional tradition, the focus has been on sentences and not so much on single words. The meaning of the predicates, the basic predicates, has been taken for given. Okay, so that's... Please interrupt me if I'm too quick. Aaron.
Could I ask a question about the previous slide where you... the slide with possible worlds.
Yep.
And I got thrown by the word intentional because I normally think of that stuff as extensional. There are objects, sets of objects, and so on. And in intentional semantics, we'll talk about something like procedures for identifying those things. Now, that may be totally relevant to what you want to say, but I just wondered whether you deliberately chose intentional as opposed to extensional for some reason that I don't understand.
As far as I see, this is the tradition in the area. I mean, this is spelled with an S, not with a T. Now, that's a tradition. I mean, for me, this is the definition of an intentional semantics, that you have possible words. Maybe there are, yeah.
In terms of Frege's distinction between Sinn and Bedeutung, sense and reference. But maybe we should talk about that later, if it's still relevant. It may not be.
Sinn and Bedeutung is important, interesting here, because I think that most people thought that by doing this intention, we got the Sinn, not just, but the Bedeutung was the extensional stuff.
Okay, so we're agreed.
No, I mean, no. I think that in analytic philosophy, maybe somebody wants to protest here, this is an interpretation of what Frege meant by Sinn.
But a wrong one.
A wrong one, yes, I agree. I agree, yeah. Okay. So this is maybe why it's been called intentional. Okay. So, next question. How can meanings be learned? And as I said, in the symbolic approach, this is a real problem. And I will get back to that. And I will show you later how we can handle the learning problem in a geometric approach. I mean, I will leave it here. I mean, I said that it is a problem for the symbolic approach. It is a problem for the neural networks. They can learn things, but in general, they learn things too slowly to be cognitively realistic. Next question. The social one. What is the relation between the individual speakers and the communal language? And here we have in philosophy a famous paper from Putnam, where he says that meanings ain't in the head. And his idea is that, I mean, he's protesting against the cognitive, conceptual analysis of meanings. He says that I know that elm and beech, if it is elm and beech, are different kinds of trees. But I'm a very bad botanist. I can't tell the differences. For me, they are just trees. So in my head, they are all similar. But I know that their meanings are different. So meanings can't be in the head. That's his simple-minded conclusion. And so he goes for some kind of realistic semantics where the experts are defining the meanings, and then we have to learn what the experts mean by the meanings and so on. I don't like this way out. I agree that we can't know, everybody doesn't know the difference between the meaning of an elm and a beech, but there is still some kind of cognitive structure to it. So, my approach is that we are communicating. I have some ideas about what trees are. You know what elms and beech are. You can tell me the difference, and I can learn the distinction. By communicating, we come to share a semantics. And I would talk about this as an emergent semantics. So if everybody has their own mental space, cognitive structure, how can we talk about something being the meaning of something? I mean, that's the general problem. And for me, semantics is a product of communication. Semantics doesn't exist before communication. It's a product of communication. And, well, it's communication and interaction with the world, so it's a combination. Meanings emerge in the heads. But when we have to share meanings, we have to follow certain rules. There are constraints on how we can share meanings. And for me, we can describe these constraints in geometric topological terms. And I will get back to that problem. So my approach here could be said to be a socio-cognitive approach. I'm still buying the idea that we have meanings in the heads, but we have to interact with the meanings in the heads of others. So my simple-minded picture here is that this is one individual who has his connection between language and meaning. This is another individual who has her connection between language and meaning. What we need to define is how their meaning structures can meet, how we can find some kind of connection between these. And this question has, unfortunately, not been treated very well in cognitive linguistics. There are people in philosophy like Stolnacker and Lewis who've done language games. They started a tradition of language games, and that's taken up some kind of tradition.
Isn't it essential to your argument that those two worlds be the same?
Sorry, they should be the same, yes. That is essential to my argument. The picture is badly drawn, I'm sorry. It was just copy and paste. So, okay, it should be the same world, and it is essential, yeah. Well, fiction is probably a problem here, but and if you're familiar with Geach's intentional identity, that may cause a problem here. I mean, Geach brought out a problem here, but that's another story. So, I say that meanings are in the heads, not in the head. That's my reply to Putnam. But I'll show you how to model this in a while. So, what is the relation between perceptual processes and meaning? Ray Jackendorf, a long time ago, wrote a paper with the title, How Can We Talk About What We See? No, that wasn't the title, but that was the question, I'm sorry. Anyway, how can we talk about what we see? I mean, we perceive things, we categorize things, and we talk about them. How does this process work? Well, the brain is multimodal, have different codes. We know that we have two different memory systems, we have different codes for vision, language, and music, and so on. And we can translate between these codes. I can talk about what I see. I mean, can put names. And if I tell you a story, you can form an image of what I'm talking about. I mean, I'm telling you, you form an image, you can also question about what was happening, making inferences from these images. We don't know how it works. That's one big problem, to know how the connection between perception and meaning works. Now, in cognitive semantics, people try to solve this problem by introducing the theoretical construct of image schemas. They are simplified representations of the meanings of words. So this is Lanacker's representation of climb. There is a landmark, a vertically extended object. There is the trajectory, something that moves along the landmark in contact with it and moves up. So that's the verb climbing. I mean, this is like a movie with a number of frames and things are happening. It's a dynamic process. This is his way of rendering the meaning of climb. And then he says that we can go from climb to climber by instead. The difference is that here the temporal dimension is in focus. It's a thick line. That's his way of focusing. Here, the frame is in focus. That means we are focusing on the trajectory here. The object doing the climbing, and that is the climber. So by having these kind of visual techniques, he wants to show that there is a connection in the meaning between climb and climber. And of course there is a connection. And this is a way of transforming one meaning to another. So this is an attempt of, I mean, and of course these are kind of visually based. There is verticality, there is contact and things like that implicit in these schemas. So this is an attempt. But it's never formally developed. I mean, it's just a drawing technique. I mean, there are no constraints on what is not an image schema. That's one problem I have with the cognitive semantics, that you don't know really what can count as an image scheme and what operations you can do and so on. But anyway, that's an attempt. And they make connections to Gestalt psychology where you find these kind of phenomena. I don't want to talk about that. Finally, what is the relation between action processes and meaning? We use our understanding of what people say to do things. We transform our semantics into action. So that's another process. And very few people, except people in robotics, have been thinking about how this works. In robotics, this is the central problem of how to get an action out of a robot. I will get back to verbs, but for me, they are either results or the actions or results of actions. So in order to get the semantics of verbs, we need to understand what actions are. And there are some attempts to represent actions. One of the first one was David Moore and Lucia Vaina's representation in terms of these cylinder figures, differential equations of walking and so on. That's one way of trying to formalize an action as a kind of geometric representation. And I took a lot of inspiration from their models. And I will bring in the forces as an important part here. I'll get back to that. This is my way of analyzing actions. So that's something about what I mean by a semantic theory. A semantic theory should be able to answer all these questions about the ontology, the semantic mapping, the learnability, the social side, and the connections to perception. And I have these 6 criteria for a semantic theory. And of course, you know all now the answer. My theory explains all the 6 criteria, but I have to spend a couple of hours to convince you about that. So, now we get into the basics of my theory. And that is what I mean by conceptual spaces, and in particular the notion of a domain. So, my previous book, Conceptual Spaces, 2000. I'm sorry. Thank you. A conceptual space is a space, and it has a number of dimensions. I already talked about the color space, the size space is one, shape space, weight space, position space, temperature, force, and so on. I don't have a finite list of dimensions or spaces here, but I'll give you examples. So that's a lack in my theory. I can't really define what goes into a conceptual space and what doesn't. What is important for me is that these dimensions have some kind of topological or geometric structures. And I already gave you the examples of the color space. What is the underlying structure, so to speak, the cognitive representation of how colors are more or less similar to one another. So here are 2 very trivial examples. We think of time as isomorphic to the real line. There is a future, hopefully it's infinite, and there is a past. Maybe it's not infinite, but from our point of view, it's more or less the real line. While we think of weight dimension as isomorphic to the positive real line. We don't talk about negative weights. So there is a difference in the geometric structure of these 2 dimensions. We represent them by numbers, but we have to keep track of the fact that weights don't come with negative numbers. So that's a difference. It's a fairly trivial one, but still to give you an example of what I mean by differences in geometric and topological structure. For me, it's important that we can sort them into domains. And domains are bundles of dimensions that go together. So the color dimensions form a domain. The ordinary spatial dimensions, I mean the 3 dimensions of our space, form a domain. Shape space, I don't know what are the dimensions of shape space, but that's probably a fairly complicated structure, forms a domain, and so on. And the domains are independent in a particular sense that I don't want to develop now. We can talk about it if you like. Take it for granted that they are sorted into groups, and I call these groups the domains. And I'll get back to domains quite a lot later. And of course, in a space like that, less distance means more similar. If you have two objects that have weights that are close to one another, they have almost the same weight. Their weights are similar, and so on. Of course, if you have many domains, which many concepts have, then you have to weigh the domains together, and that's a separate problem. Now, here is my key idea, and let me just finish this. And that is that in a space like this, you can talk about regions. I mean, there is closeness, there is similarity. And for me, a concept is a convex region in one or more domains. So this notion of convexity is very central for me.
First question was, do you think the domain is just a product of those dimensions? And are the dimensions always a subset of a real line?
Answer to both questions is no. In the color case, that's why I gave the color case. It's not just a product of the three dimensions. First of all, one dimension is circular. It's not a real line. And it's not a product because they form a double spindle. So it has a constraint on the product space. And that answers your second question as well, because not all dimensions are isomorphic to the real line. I can even have graphs as dimensions. That's perfectly okay.
So your notion of convexity is somewhat more general than in mathematics in general?
No, my notion of convexity depends on the notion of betweenness. And on the real line, of course, you have betweenness. But you can have betweenness in graphs as well. You can have betweenness in lots of ordinal structures. So it's more general than what you mean by convexity in real products of real spaces. But the only thing I need is that the dimension. You can talk about betweenness for the dimension. That's all I need. And you can do that for a lot of other structures than real lines. Okay. Good. So, color spindle again. Meaning of red as a region. Convexity simply means that if this point is called red and that point is called red, then anything in between is also called red. It doesn't matter that the borders may be vague. I mean, you may have degrees of membership in the red domain or whatever, but as long as you say that this belongs to red with a certain degree of membership and that belongs to red with a certain degree of membership, then anything in between should also belong with the same degree of membership. So vagueness and convexity, no conflict. That works fine. Now, convexity is a hypothesis here. And when I wrote this book, Conceptual Spaces, I made a prediction that natural languages carve up the color space different ways. Some languages only have two color words, basically light and dark. Some languages have three color words, light, black, and light, dark, and red. And some languages have 11 color words. I mean, you have different ways of carving it up. And some of the borders don't overlap and so on. But I made a prediction that in any natural language, any color word denotes a convex region of the color space. And at that time, I only knew a few languages, and I had good support for it. I'll get back to that prediction in a few minutes. But you get an empirical prediction from this notion of convexity. You can test it by looking at what is the meaning of color words, for instance. So I will remember these words, domains and convexity, because most of my talk will be centered around these meanings. So, why convexity? First thing is that it speeds up learning. You remember that I had a problem with telling you how we can learn the basic predicates. So my idea is very simple here. I give you a basically naive model of how you learn things in a conceptual space. So, to tell you a story, imagine you're a father and you have a 3-year-old daughter you bring to the pond in the city, and there are these ducks and geese and swans. And you're pointing to this object, you're saying, no, this individual is saying, this is a duck, but that one. No, I'm presuming that I have a conceptual space. I mean, all the properties, all the domains of a duck. And I reduced them to a two-dimensional space here. I mean, it's just for illustration. The child looks at the different animals, see their colors and the shapes and sounds and whatnot. And this is my representation in the two-dimensional space of one duck. That is a goose and that is a swan. And there are different kinds of ducks, there are different kinds of geese, there are different kinds of swans. And you see a number of examples. So you say that this is a duck, that's a duck, and that's a duck. And then, in the child's mind, I mean, there you see the similarities between the different objects. You form some kind of average. And this average you can call a prototype, if you like. And that may represent something that you haven't seen. But I mean, you can, if you have now I'm making the assumption we have a metric space. That's, this time I'm assuming we have a metric space. In general, I don't assume metric space. So we can, average presumes that we have a metric. So we can form the picture of the average duck, the average goose, and the average swan. And on top of that, we can then add what is called the Voronoi tessellation. And the Voronoi tessellation is depicted here by these lines. And these lines are defined as the midpoint in between the crosses. So this line is defined by being equal distance to the two crosses. That line is defined by being the equal distance to these two crosses. And that line is defined by being the equal distances to these crosses. And it turns out that if you have this simple rule, you get Voronoi tessellation always results in convex regions. It's a two-line mathematical proof. So the point is here that given a couple of examples, you can form an average. On the basis of that average, you can generate the Voronoi tessellation. And so basically you only need one example to form an average. Because if you've only seen one duck, you think that that's what ducks looks like. So soon as you have heard the word duck once, you have one point in this multidimensional space that you can use for further reference in comparing it to duck and geese and so on. So basically, one example is enough to start this process. What's happening here is that learning is not finished. I mean, you've seen 3 ducks and 3 geese. Now you see a new duck, a new bird. It looks a bit strange. And according to the old classification, you would classify it as a goose. But your father, or the child, would classify it as a goose. And the father insists, knowing more about birds, that this is, in fact, a duck. And what happens now is that the child has to adjust its meaning. He has to accommodate the meaning of duck. So the average would move a little bit of what you've seen. And consequently, the borders between the lines will move as a result of experience. So for me, the meanings of words are not fixed. They can't be defined by necessary and sufficient conditions. They are dynamic, and they are dependent on the communication. In this case, the father is the knowledgeable person. So he can impose the meaning of duck on the child. The child has to adjust. In other cases, we fight over the meaning. No, is this shirt red? No, it's cerise, it's not red. And we fight over the meanings of the borders of color words, for instance. And that's well, then we have to decide. Yeah.
Thank you. I'm wondering, are you committed to reifying this average, as opposed to, for example, using a case-based representation where you would take the exemplars and they would collectively represent the concept, but you would never actually reify the average?
I can imagine models like case-based reasoning where you handle similar problems. I only did this as a very simple exercise to show that to get the Voronoi tessellation and so on. I mean, talking about average distances and so on. So I mean, this learning model is compatible with this learning idea is compatible with other models, but I'm using the spatial structure here. Because even in case-based reasoning, you need a model of similarity. You need similarity for case-based reasoning as well. So I mean, this is a baby example of learning. I mean, I'm not saying that this is the real example, but as a matter of fact, it explains a lot about how children learn concepts. If they've only seen cats and dogs, and they come out and on the countryside and see a horse, what will they call it? A dog, because it's more similar to a dog than a cat. So this explains the overgeneralization of concepts. So if you only have a few words, you call it by the words you have available.
Could you maybe briefly elaborate on how this fits with semantic chaining, where we have categories that are not convex, but like new elements are added to a chain, which is quite well attested in linguistics?
Of course. This process is not perfect. Sometimes you end up with an object that doesn't fit with the pattern. So you end up with something that wouldn't be convex. My way out of this problem is to say that in most cases you create a new concept when this happens. So this idea of convexity drives your need for new words, so to speak. This is not a perfect story. We can get into the details, but I don't want to do that. But I mean, I will defend this convexity idea quite strongly, and I hope you can come up with good counterexamples that we can discuss. You want to say something?
I'm wondering whether this is supposed to apply to all concepts or only perception-based concepts. The reason why I'm raising this is that there are concepts like those in modern chemistry, where instead of organizing things on the basis of their appearances, as we might have done in the past, we organize them on the basis of the theory as about their structures. And that doesn't give you this kind of space where you have metrics and whatever. It needs a different kind of mathematical analysis. And grammars in language would have similar properties.
Thank you very much for the question, because that's very important. Most of my examples I give are based on perceptual mechanism. I mean, I will talk about forces as one case, and we don't see the forces, but we almost see the forces, and I'll explain why. Yeah. And your point is very good, because when we get to abstract concepts or scientific concepts, this process may break down. But for me, what I want to model here is how a child learns a language. Then when we get up, where we use language to define new concepts, then, I mean, as in science perhaps, or in abstract things, this model may break down. But I'm happy if I can do the basic perceptually or action-grounded concepts. I think Ben was first.
I just wanted to offer a couple of non-convex color terms, like intense, which is easily expressible in your spindle as a sort of torus around the outside, or primary, which would be a sort of Y-shaped structure pointing to the primary colors.
Okay, yeah. Intensity is no problem, except that I have to leave the Euclidean metric and instead introduce a polar metric, and actually that's how we do it. So if you have the circular dimension, and if you take the angle as the defining, then intensity would be a convex region in polar metrics, and actually that's what I want to do. Primary is a tough one, and that's an abstract thing. You can't learn what a primary color is without hearing it given in language. That's an example, a good example of a concept, of a concept that you have to learn via language. You don't think that's correct? Okay.
Yeah, there's been some very interesting anthropology that was done by starting with Eleanor Roche many years ago, looking at the languages that have different collections of color terms. And when they do have color terms, they introduce the primary colors basically one by one.
What you're talking about is what they call focal colors. Yeah, and the focal colors, there is an agreement. I mean, in all cultures, people agree on what is the more typical red. And there are not so many focal colors. I mean, there are basically, so, I mean, green and blue, I mean, people disagree a lot about what is focal in green and blue. I mean, there is no agreement. But there are a few focal colors, and I'm not sure about the empirical evidence here.
So you could substitute focal for primary.
Yeah, but then your case becomes weaker, and we should discuss that. Okay.
I just wanted to react to Aaron's point. Seems to me one of the selling points of your approach, which you haven't emphasized, is that it would explain why we use metaphorical terms. When we have more abstract ideas, we often use geometric metaphors to explain them, and so I think that would explain why, how we can take these ideas forward into non-perceptual concepts.
Thank you very much. That's exactly the way I want to go by using metaphors. We understand abstract notions by using metaphors. And I have a little bit of analysis of metaphors, but I get to that later. And metaphors means simply mapping between domains, mapping, structure-preserving mappings. That's what metaphors are about, yeah.
So when you explain that the intensity can be made into a convex region, you say that you just change the metric so that it becomes a convex region. So it seems that there is a certain kind of circularity, that the metric is defined by the concept and the concept is defined by the metric. Another example I would like to give is in temperature. Like if you have a warm temperature, that's obviously a convex region if you order the metric by the warmness, but a dangerous temperature, which can be either really hot or really cold, becomes convex if you order it in terms of how dangerous it is. And in general, of course, if you order, or if you think about shapes and skewed, like if something is skewed, then it's not straight and it's not horizontal. That's a not convex concept in terms of the angle. But again, you can put a different metric so it becomes convex and so on.
Thank you. Well, I shouldn't thank you for accusing me of circularity, but anyway, thank you for the point. No, there is no circularity here. The question is, how do people judge similarity between colors? And I haven't done the analysis. I've done it. I'll get back to when I get to prepositions, because in prepositions I will also use a polar coordinates. But if you look at similarity, you will find polar convexity. This is my prediction. So I would ground everything on judgments of similarity here. The metrics, the notion of betweenness and so on the judgments of similarities. So there is no circularity. Then verifying this empirically is a tough task. Dangerous temperature is, there are some examples of negative concepts that are actually, you have a central part, and then you have the two outliers. So these negative concepts are non-convex. You're perfectly right about that. My way out of this, and it's not a perfectly good way, is to say that you can't learn the notion of a dangerous temperature or these negative concepts without knowing the central notion first. So this is a case where you use negation to create a new concept. But my prediction is that you have to have the positive case first. I'm not sure about, I mean, dangerous temperature is a bit odd to me, but anyway, yeah.
Yeah, well, in defense of convexity, there have been a number of PhDs lately on quantifier terms like many and few and color terms, where if, on the emergence in populations of agents, right? And so if they did not have this assumption of convexity, the languages that would emerge in these experiments would not look at all like the concepts that we find in natural languages. So these PhDs one by one confirmed that you needed this kind of assumption to explain something about human languages.
And my short answer to that is otherwise they wouldn't be learnable. I mean, that's the point. I mean, there are too many concepts. You need constraints, otherwise you can't learn them. And for me, this convexity is a very natural, and it, as I show it, will do a lot of work for me. Okay. That's the first answer, that convexity makes learning more efficient. Second answer, it connects to prototype theory. And I already gave you that one example of saying that the averages are the prototypes. Eleanor Roche was mentioned here. She said that there are more or less typical examples of duck and geese and of furniture and fruit and vehicles and whatnot. If you have some kind of space, maybe bird space, it may be color space, it may be whatever. And you know what the prototypes are. And if it is a metric space, I mean, Voronoi tessellation depends on the assumption of metric. Then the prototypes will generate a Voronoi tessellation. And the important point here is that prototypes generate a form of cognitive economy. Once you've seen a number of examples, you don't have to remember all the examples, unlike case-based reasoning. You can do with remembering the prototype. And once you remember the prototype, then you can generate. When you see a new object, if you see a new object that fits here in the space, my pointer is that, if it fits here, then it's closest to this prototype, and you will name it by this prototype. So having prototypes is a case of cognitive economy. It takes off your memory resources. And case-based reasoning doesn't do that well on that point. I mean, having a single average here is very economical from a cognitive point of view. Okay, so that's a second reason for why you want to have convex representations. I will get back to this point later when I get to adjectives. But there is actually very strong support for the color categories. They do, so I'll get back to that. Now, in propositional logic, you make a distinction. No, you don't. You only have predicates. And predicates, if you translate them into natural language, they stand for nouns, adjectives, verbs, prepositions. They stand for all the different word classes. I divide the predicates into two basic categories here. One is what I call a property. And a property is a convex region in a single domain. So a color is a property, a shape is a property, a size is a property, a weight is a property, and so on. While concepts is configurations, are things that have meanings in several domains or connect several domains. So it's a set of convex region in a number of domains. Well, I mean, number could be one here, so property is a subclass of concept here. And I talk about the prominence value of the domains. Some domains are more or less important here. And the other part is information about how the regions are connected. There are correlations between the domains. So let me give you an example of, this is again a baby example. I'm not saying it's a full analysis, and I don't think we can have a full analysis. What is the meaning of an apple? Well, an apple has a color, a taste, a shape, and then you can add further dimensions like nutrition and so on. But when you're a child, you learn what apples are basically by shape. Apples are different from pears and apricots in shape. They have a particular taste, and you learn sooner or later that apples come in red, green, or yellow. They don't come in blue or black and so on. They cover a certain domain. So you learn the meaning of an apple and then as you get older, you may add further dimensions. I mean, this is another part of learning more about concepts. I mean, you add new domains to a concept. You learn that they have vitamin C and so on when you learn to understand about those things. And if you really become a scientist, a pomologist it's called, then you learn about the flesh type and the seed type and the peel type and so on in order to classify the different kinds of apples. You add further dimensions to your knowledge.
Sometimes the addition of these properties actually change your conceptual space. And so, I mean, if you think about is a whale a fish, originally you're paying attention to its shape, the fact that it swims in the sea and so on. And when you change it to mammal, you're paying attention to a different set of properties. And so it's not just adding properties to an existing concept, but actually changing the concept.
Thank you for the example. I had a slide with that exact point, but I deleted it in course of time. But it's a very good point. And that has to do with the prominence thing. Let me get back to that. But anyway, let me say something. I mean, how do we model these models? Yeah, color space I've already talked about. And now we get back to this convexity, actually. Red, green, and yellow form a kind of half circle of the color space. In the middle of red and green is gray. But we don't see gray apples. We don't expect to see gray apples. This forms a convex region, red and yellow, actually. Taste space is 4-dimensional, or maybe 5-dimensional if you want to call include umami taste, but there is sweetness, sourness, bitterness, and saltiness. And when it comes to apples, it's mainly sweet and sourness that matters, and so on. Shape space, I don't know. I mean, there are theories about shape space. I don't have a good mathematical model. I don't know how to represent the dimensions. But basically, there are round things. Apples are not perfectly round. They're a cycloid or whatever they're called, but they are different in shapes from pears. Otherwise, apples and pears are quite similar in terms of color and taste and nutrition and so on. But they are distinguished from pears in terms of shape, basically. Here is shape space, according to Marr. Again, he was the first one to do this. And what he did was to give good arguments for why we should break down a shape into cylinders, or more generally into generalized cylinders. And then we can represent different shapes in terms of how these cylinders are combined, the sizes and the proportions and so on. So that's one theory of shapes, and it's dimensional. Each cylinder can be described by 2 coordinates. If you have a generalized cylinder, you can describe it by 3 coordinates. But that means, anyway, this is a hierarchical vector of coordinates. So it's a vector representation of shapes. It's not perfect, but it's a first approximation, and I like it because you can describe it as a conceptual space. Okay, that was what I wanted to get into in terms of the basics. Now I want to say something more about the there was something I would... Okay. Yeah, the prominence. I think I want to say more about the prominence later. Yeah, I'll skip that at the moment. Okay, here's the question. A 4-year-old can understand the meaning of the color words. You can teach the 4-year-old chartreuse and mauve quite easily. These are very odd, unusual color words. But it's more difficult to teach them the words inflation and mortgage. And this is not a matter of frequency. In natural language, these 2 words are much more frequent than these up here. So this is not a question of frequency. My explanation is that the 4-year-old has internalized the color domain and color words. As soon as you say that these are colors, and then you can say that chartreuse is a kind of yellow-green and mauve is a kind of light violet or whatever it is, they can understand what is the meaning of the terms because they have the domains available. Now, inflation and mortgage depends on the abstract domain of monetary value, and they don't have it in general 4-year-olds. So for them it's difficult to explain these terms. Even if they're very frequent in language, they don't have the domains available. And my point here is that we are not born with the domains, we learn them. Some of them, we are prepared for some of them. I mean, the color, if you're not colorblind, you will learn, you will pick up the color similarities and so on after a while. You will pick up the shapes by interacting with the world. You will pick up distances and sizes and weights and so on by your interaction. But you have to learn to separate these domains. But language learning or understanding depends on that we are sharing semantic domains. And when you start talking, Aaron starts talking about chemistry domains, I mean, we wouldn't understand them because we don't have the background to understand what's going on in these chemistry domains. We don't share it. So I will say a little bit about early domains in childhood learning. And one is, of course, emotional domain. We don't talk in language about it very much, but it's important when we value things, when we decide whether we want to act or not to act. And there are many theories of emotional space. This is one of the more well-known. I think it's called the Russell space. There are 2 dimensions of pleasure and displeasure, arousal and high arousal and low arousal. And then you can place most of the normal emotions in more or less a circular structure here. There are some emotions like shame and guilt that don't really fit in here, and they are depending on some kind of social interaction as well. So it doesn't cover. But anyway, that's something we learn. I mean, we have bodily reactions along these two dimensions. We learn to categorize, and we learn to read the expressions of the emotions in other people. So that's part of actually of our mind reading, of the theory of mind, that we learn this emotional domain. We learn the visual spatial domain. I mean, learn to orient ourselves in space. We can judge distances and angles and so on. But I want to make a distinction between egocentric space and allocentric space. And for people in robotics, this is well known. I mean, egocentric is space with yourself in the center. Allocentric is independent of yourself. And it takes some time before they can learn allocentric space. Piaget was one of the first who looked at that kind of distinction. So, I mean, there is not only one spatial representation. There are at least two, maybe more. Action space. I will get back to that. And I already showed you this picture from David Marr. And my take on it is that we classify actions by forces, the forces that we exert on our body, and I will explain this part to you later. So the force domain is important for understanding actions, and for me, an action is a pattern of force vectors, and a pattern can be described as a hierarchical vector. But that's as you see, I mean, Marr has this hierarchical body shape. I want to say a similar thing about actions. They are also hierarchical patterns over time. Object category domain. I talked about the distinction between properties and concepts. And object categories have different properties. I mean, now, let's start with physical objects. I mean, we can talk about abstract objects later, but in general, physical objects have size, shape, weight, color, taste, temperature, and so on. And I define them as convex regions or domains. Categories is what I call, well, it's a special case of what I call a concept, sets of properties plus correlations. So that's, I will get back to the object category domain when I talk about nouns. Okay, I can already now reveal to you that the basic distinction between adjectives and nouns as word classes is that an adjective in general denotes a single domain. A noun denotes a product of domains. So adjectives correspond to properties, nouns correspond to concepts or object categories, if you have object nouns. So this distinction maps onto a basic distinction in lexical classification. But I'll say more about that after the break. Goal space is also important. We want to read the intention of others. And the first kind of goals you have is to move from place A to B, or from the start to the goal. And what happens is your goal space is your internalized vision of, I'm here now, I want to go there. So I form this goal of moving here, and I may encounter obstacles and so on my way. But, I mean, this is a simple problem in robotics to form this goal vector. So what you do is basically you transform your vector in space into a vector in goal space. When your goal is a spatial, it's a very simple transformation. But you can extend it by metaphorical mappings. Now we get to, I have a goal to lose weight. So now I'm now at 89 kilos, and I want to go down to 85 kilos, say. So I have, my starting point is a point on the weight scale, and I want, my goal is that. But it's still a trajectory in a space. So, I mean, it's a kind of metaphorical thing. Okay, so now I've given you some examples of the spaces that we learn as a child. We learn to handle all these spaces. And, I mean, I haven't given you the property spaces, color and size and weight and so on. I mean, they are. But the emotion space, the action space, the goal space, the shape space, they are very central for learning basic languages. You need goal space for all the intentional expressions. And I will not talk very much about the intentions here, but anyway. Okay. that's the general survey of conceptual spaces and semantic domains. Now, I will spend some time on this semantics as a meeting of minds before I get into the lexical semantics here. People think that all words should be given a similar analysis. But I want to distinguish between two semantic processes. There is a passage in Wittgenstein's Philosophical Investigations that he says that words are like the handles in an engine, and all the handles look alike, but they have different functions. And all the words look alike, but they have different functions here. That's my point. And my basic distinction is between a fast and a slow process. And a fast process is the one when we are coordinating our meanings while we are talking. And joint attention may not seem as a case of coordinating meanings, but actually that's fundamental. We have to look at the same thing in order to talk about it, in order to interact about it, and so on. And that doesn't seem to be part of semantics because there are no words involved in it. But I say that this is very important, that we can coordinate on the same thing. That's the most basic form of meeting of minds, that we look at the same thing, that we have joint attention here. And then common ground, that's Herbert Clark's notion. And then we have the slow coordination of words, and that is when we learn the meanings of ordinary words, like nouns and adjectives and so on. And actually, there are some word classes that work with the fast process. Pronouns and determinants, demonstratives, and so on, they change the meaning each time I say it or he or she. It may change meaning. That's part of the fast process. While when I talk about snow and green and horse and so on, that's the part of the slow process. But we are negotiating meaning, we are coordinating, we are maybe learning a bit about the meanings. Okay, Clark talks about participant in a conversation. They have a shared information. When I meet somebody, it may be part of my family, then we have a lot of shared information. It'd be part of my workplace, we have some shared information. If I meet a person here in Edinburgh, we have some shared information, but not perfect. But as we talk, we accumulate. I mean, part of this discourse process is to build up a common ground. And we can refer back to what we've been talking about by pronouns and so on. And this is part of his thesis, Herbert Clark, that speakers design their utterances so they can identify what is to be added to the common ground. And there are lots of repair things. If I say that she walked in the wrong way on the street, you may not know whom I mean, so you ask, who is she? And then I have to tell you more, so you can identify this she. We can find a common ground on the reference of this meaning of she. So there is an interaction in building up this common ground. But normally we choose pronouns, so it's fairly easy for our addressee to understand who we are or what we are referring to. And that's part of what I call the fast process here. Yeah, okay. Now I get into my fourth reason for convexity here, is that your representation of the meaning of a word may be different than mine, and we have to coordinate. And the point I want to convince you about now is that if we assume that your representation is convex and my representation, that will help us in coordination. That's the fourth reason for convexity. And now I get into, this language game style of analysis that some of you may know of from Lewis and Stolnacker and later developments. So I will tell you about the language game here. But the difference between me and the earlier tradition is that I'm assuming that our meaning spaces are geometrically structured. In the old tradition, there is no such assumption. So I will add this assumption about the geometrical structures here. So Robert is sitting at the back row here, Robert van Rooij and Gerhard Jäger. They developed a communication game. I don't know if you will talk about it later, Robert, in your talk. Maybe, okay. So let me try to describe it and hope you agree with it. What you have is that they assume that you have a common space for colors. And actually you assume that they have identical spaces. And then the idea is that, let's see, the signaler sees, the computer or nature picks one color, one point in this space. And your task is to send a message to the receiver. And the task of the receiver is to pick a color in his space. And the closer you are in the real color and the one the receiver picks, the more reward you get. I mean, it's a cooperative game, and you need to find colors or points in the space that are so close to one another as possible. And the signaler has a finite, it's an infinite space. The signaler has a finite number of messages. And you have 2 messages, 3 or 4 or 5. And so the color space is say a circular space. You have 2 messages. You can say A or B to the receiver. And then the receiver has to point to one place in color. And you're rewarded by the distances. And what they show, Jäger and Roy, I've said it's minimizing the similarity to the color, is that there is a Nash equilibrium of the game. I mean, you do this, you simulate it on a computer and run it until you get some kind of fixed point. And the Nash equilibrium turns out to be Voronoi tessellation, all regions convex. And if I go back to the picture here, what you see here is that certain points turn out to be kind of prototypes. So whenever nature picks a color, this point, the receiver signaler says A, and the best answer for the receiver is to point to this central point here. And this central point is defined by the fact that it minimizes the average distance to all the points in the area. So minimizing the average distance means maximizing your average reward here. But the Nash equilibrium always results in a Voronoi tessellation. Now these points may be located wherever. I mean, there is no unique position. But as the process runs, they will emerge. If you have 2 messages, there will emerge 2 prototype points. If you have 3 messages, there will emerge 3 prototype points, and so on. So the number of messages defines the partitioning of the space. Is that a fairly correct description, Rob? Yeah? Good. Now, what I did so these points, I'm sorry, these arrows are not perfect, but these blue arrows are the original points, and they should point then to this prototype. And what the receiver sends back is to point to this prototype. Here, the spaces are identical. But these prototype points, they function as fixed points in the communication. If I say A, your interpretation is that it is the prototype, and you point to the prototype. So that is a fixed point. I mean, if nature happens to choose this point, it will come back, and the receiver will point to this one. So the fixed points then help you. Once you have the fixed point, you can generate the Voronoi tessellation. You know what to call a new thing, as I described earlier. Now, I extended this model that we got from Jäger and van Rooij here together with Massimo Valli into a more general model. We are no longer assuming that we have the same mental space. They can be the only assumption we make. Well, I get back to the mathematical model. There are some mathematical assumptions about it. But what we have here are 2 linguistic functions. One is the expression function. You take something you want to say, I mean, a particular color. You use a word to say something about it. So there is a function from perceptual input to linguistic output. That is the expression function. And the converse is the interpretation function. You hear a word, and then you have to interpret it. So the expression function is to point to something, point to color something, think of something in the world, have a mental representation of the meaning of. It's the other way around. I'm sorry. It's miswritten here, but you get what I mean. Yeah. Okay. I'm sorry. It's I misnamed them here. Okay. Sorry. Anyway, normally we do this via language. So I have my color space or whatever space I want to represent. I have a language containing, I mean, language is discrete. You have words there. You have to pick one or maybe a sequence of words, a discrete function. And then that filter results in some kind of understanding in the conceptual space of speaker number 2. It doesn't have to be language. It could be pointing. I mean, I can start pointing at something and you look at the thing. And if we have joint attention, we have a fixed point. And actually, that's what's happening in joint attention. We're creating a fixed point. Joint attention means that I point at something, you look at what I'm pointing at. I see that you look at the same point, you see that I look at the same point. So that is a fixed point in communication. We're doing things, we're coordinating ourselves on a point in the real world. So joint attention is a good example of this kind of fixed point procedure. And here, my pointing is continuous. I can choose any direction. I don't have this finite. I mean, language is discrete, but it's combinatorial, so you can make a lot of combinations here. What's happening? Well, yeah. One assumption is that the best way of doing this is that if 2 points are similar here, or close to one another, I should use the same word. Otherwise, it's difficult to communicate. So the fixed point semantics says that, yeah, well, it's like reaching an agreement on a contract. A semantics is a product of these 2 functions. Mapping my impression onto a linguistic expression or some kind of communicative act, it could be pointing, and then mapping that back to some kind of content, again, a point in the conceptual spaces. So semantics is a product of the expression function and the interpretation function. Yeah, and minds meet when we find this fixed point. So declarative pointing, yeah, joint attention is an example of this fixed point. And in communication games, you have equilibria. Yes, this is also an equilibrium, but what we add here is the topological geometric properties. In general, you don't know. There may be many equilibria or no equilibrium in a communication game. I will show you that by assuming something about the properties here, we can know that there exist fixed points. So, and I also would say that there is the same mechanism in fast and the slow process. I don't want to get into the details here. I've given you examples in pointing is an example of the fast process, but understanding the meaning of a word is an example of the slow process. Now, 2 minutes of mathematics. States of the minds are product space of the individual mental representations. I have my space, you have your space, we take the product space of that. The interpretation, the semantic function, the product of the interpretation expression function, is a mapping from the product space to the product space. Similarity provides a metric structure. Now, okay, we're actually assuming that we have a metric structure to each of these. And the only thing we assume about the spaces is that they are convex and compact. Fairly general topological assumptions of the individual spaces. And the product space will also be convex and compact. Well, there may be more than 2 speakers. We may have any community of speakers. We can talk about a number of speakers. And then that is the product function from the product space to the product space. I already said that. And we assume that this function is continuous. What continuity means is that it's preserving similarities. Close enough means similar enough. Continuity means that language preserves similarity relations. If you use words, if you use a word, they denote a set of similar things. So that's the meaning of the continuity assumption of this function. Now we can apply a fixed point is a point as I said earlier, that maps back to itself. Mathematically, it's like this. We can apply Brouwer's theorem here. Every continuous map of a convex compact set on itself has at least one fixed point. So we know that it exists. If our minds are convex and compact, we can meet. There is at least one fixed point. We don't know how it looks like, but we know it exists. As I showed you, the set of prototypes, they define the fixed points. I mean, that's in their game, you get them as the prototypes. But we are generalizing this to a more general framework. The spaces don't have to be identical, but as long as they are convex and compact, there will be a fixed point. So the semantic interpretation of this result is that if individual meanings are well-shaped, in the sense that we all have convex regions as meanings, and language is plastic enough to preserve the spatial structure, that is the continuity assumption, there will be at least one equilibrium point. Now, as the Gärdenfors example shows, that we may end up with any number of fixed points. I mean, starting to communicate doesn't mean we end up with a particular semantics. We can have lots of meaning mappings, but we know it exists. We know that if we negotiate long enough, adjust our meanings, we will find a fixed point where we mean the same thing by the same word. It corresponds to I can't say the same region, because your region may be different, your space may be different from mine. You may have different regions, but we will have the same fixed points at least in our spaces. So I'm not saying that your understanding of red is exactly the same as my understanding of red. By the way, I'm partially colorblind, so that's fairly obvious. But it still works because they're close enough, and the mapping is fairly good. So this is my more formal analysis of what I mean by meanings are in the heads. They emerge via these interactions as fixed points in these semantic mapping functions. And of course, they emerge through interactions. Where speech acts move, we try to coordinate and negotiate our meanings. There is a slow process, there is a fast process in doing this. Of course, we never reach the fixed point. Language is always fluent. We are learning new things. We are changing the meanings of words and so on. But it's an ideal. But we are close enough to the fixed point that most of the time we succeed in our communication. And I've already said they exist because our conceptual spaces have the right structure. Now, the question of order is that this is all mental. You have your mental space, I have mine. We discuss. We can sit and talk about a novel, or you have read a book, I've read a book. We sit and talk about the characters, and your understanding of this character and my understanding of this character, and maybe we agree. We understand why they did something in the novel. It's totally fictitious. So where is the world? Where is the external world? Has to be some kind of feedback from the world in order for this mapping to make sense. Well, in the Gärdenfors example, there was a payment, there was a reward for how close you got in your interpretations, and in our interaction, there is a reward by succeeding or failing in cooperation. We start talking about doing this, and so the reality enters via the payoffs of communication. If meanings is not aligned with reality, the communicators will suffer costs. Let me give you a trivial example. I have been on a very bad telephone line. I mean, I'm off on a wild island, and we agreed to meet in Cambridge next Tuesday. So I go to Cambridge, Britain, and you go to Cambridge, Massachusetts. We have misaligned the meaning of Cambridge here. And that will teach us that, I mean, this is an enormous cost. It's a very important meeting. We have to meet. But he ends up in the United States and I end up in Great Britain. We failed to, we used the same word, Cambridge, but we end up in different places. There is no coordination of meaning in this case. So that's an example where reality enters into the feedback here. If we fail, we have to renegotiate. I mean, you may mean something by a particular term. I don't understand it, so I don't know what you do. And success gives us a grounding in the world here. So the meanings are in our heads, but the results of the meaning negotiation process is dependent on the results in the real world. That's what drives the cost and the benefits in generating this fixed point situation. You see how I can get a semantic as the meaning of minds. Now, this result only says that it exists. Now, in order to have more flesh on the bone, we need to say something about how our spaces look like, how the words function in this communication. But I will do that after the break. So I think it's actually a good time for me to take a break. Is that okay? A bit early, because this is where I plan to take a break. I'm finished with the meeting of minds, and the next part will be more linguistic, going down into this is the philosophical part, and the next part will be more linguistic. We have time for questions then. Yeah.
In the mathematics slide, you talked about representations, while before you talked about properties and categories, and like what's the connection? And another. Oh, maybe that's the first question.
In this general model, I haven't made that distinction. It's a very general mapping, so I haven't made that distinction here. It will come back in after the break when I talk about different word classes. I mean, they are particular. Now I will split up this mapping into different partial mappings between word classes and different conceptual structures. So it will come back. I hope you will.
And first you said that the mapping is from my conceptual space to your conceptual space, and back again, but in the mathematical treatment you had a product of our spaces, my space product with your space, and then a mapping.
Let me go back to this picture. So this is my space. This is your space, and I see something. I see color here, and I use a signal. That's the expression function. You hear my signal. You have to interpret, and you have to point to a place here. What's happening is, and then you signal back. So what we have is a mapping. I'm sorry, because these two spaces are identical, so it's a bit difficult to show the differences. But assume that they were different. There will still be dark points that correspond to the fixed point. But the space I'm talking about, in order to apply Brouwer's fixed point pair, I have to take the product space of that and have a function that goes from points in the space to points in pairs. Yeah, in this case, it's pairs. Yeah, mappings of pairs. Yeah.
How is this pair of points mapped to other pair of points?
This point is mapped via that space onto that point. If I start from here, this point will be mapped via that point onto this one. This is the mapping in the product space. It has to go via the other one. So it's a mapping between, yeah. And the fixed point are the points that are mapped onto themselves via this double route. It's a bit abstract, but I hope the mathematics is correct here. I mean, we want to get it to fit with Brouwer's theorem.
Yeah. It seems that you're assuming that there will be three categories, always. Imagine that an agent has three categories and another has 4 or 7 categories, for instance. What will happen in this case? Will they sum up into 7 categories or in 3 categories?
No, in the language game, it's given that you only have 2 messages or 3 messages. That's a rule of the game. And if you have 7, you will end up with 7 different regions. So it depends on the rule of the game. More questions? Go ahead.
Here in this game, the equilibrium is found in the space of functions from the space to the space. So you're finding a function which maps red points to this and red there. While in the other slide where you have this mathematical model, the function is already given, and then you're finding a fixed point of that function. That's 2 different things, right?
Well, we should need to talk about this over the break, because the reason you can do it as function here is that the spaces are identical. But if they're not identical, you have to have this product space construction. So that's the reason. Okay, maybe we talk past each other.
Okay, actually the timing is perfect.
Yeah,
We started 7 minutes early.
Okay, we finished 7
minutes early. Okay, great. So coffee is out there and with some cake or something. And we'll start again at 11:30.
Form the basis for the vector spaces there. That approach never leaves language. I mean, it's just text-based. There is no connection to anything outside the linguistic data. But still, I mean, it's another way of representing similarities of meanings, but that's mainly statistically based, if I understand it correctly. Okay, back to my talk. Now, I get into the 4th topic here, the cognitive grounding of word classes. And I really mean it seriously, a cognitive grounding of word classes here. So, first question to ask, why do languages have word classes? And why don't we all speak propositional logic, where you only have predicates and variables, or predicates and individuals, and then logical operators? What is the point of having all these nouns, pronouns, adjectives, verbs, adverbs, and so on? Well, if you are a linguist, yeah, okay, first of all, I mean, these word classes are not universal. I mean, they come from Sanskrit and Latin originally. They are mapped onto the Indo-European languages. And if you do in non-Indo-European languages, it's kind of difficult to fit the words into these classes. So this is not universal. But still, I mean, in Indo-European languages, you find correspondences to most of these classes. And the borders are not always sharp either, even if we are taught so at school. In traditional linguistics, the word classes are defined by their syntactic properties. While once you learned these word classes at school, you were told that, well, nouns, they stand for things, adjectives stand for properties that things have, verbs are for describing events or actions, prepositions are for describing spatial relations and so on. You were given some kind of explanation what is the common meaning of all nouns. I want to go back to that. I want to take this kind of primary understanding of what is a noun. Forget about the syntax. My semantics is 100% syntax free. At least I want it to be 100% syntax free. Maybe I don't succeed. I want to do an analysis of these word classes that is not dependent on any syntactic categories. So, I want to give a cognitive communicative motivation for these classes. Let's start with nouns. And I will be a little bit simplifying a bit here by only doing object categories. I mean, there are lots of abstract nouns that I don't really know how to handle. And we talked a little bit about it already before the break. So this is the basis for nouns. I mean, not all nouns, but most nouns. And you remember my distinction between properties and concepts. So object categories are based on this concept with information from several domains. I mean, a dog has a shape, a color, a smell, well, maybe not a taste. You don't normally taste dogs, but it has a size and a weight and a sound, and it eats things and so on. There are lots of domains in understanding what a dog is. So one question is, of course, which domains are included in a category? And I don't have any really good answer to that. I have a cheating way of doing it, and that is to look at what you can think of as definitional generics. I mean, if you want to define what a dog is, you say that a dog has 4 legs. This is what is called a generic sentence. Or a cup has a color. These things make sense, but saying an idea has a color doesn't make sense. So color is not part of the noun, of the domains for of the abstract concept of an idea. But I mean, this is a indirect way of getting at what are the domains for a noun that matters. And basically, there are no sharp boundaries. I mean, as I said in the case of apples, they may be more or less domains that you include. Some of them are more central, some are less central.
The trouble with this definition is that it neglects metaphor. So climate change is a green idea, communism is a red one.
Metaphors are, yes, okay, good. They are more or less salient or essential for a category. And you mentioned this case, so I'll give you an example one. But let me just mention these generic sentences. Let's see now, I don't... okay, forget, the first row shouldn't have been there. This is an example of a generic, a madrigal or polyphonic. You can say a madrigal is polyphonic, that's a generic. You can have madrigals are popular. That's not a generic, that's a fact about the world. But you can't say a madrigal is popular. That's a kind of syntactic test for why something is generic or not. It's not a very strong test. But the point I'm bringing up generics is that they are universal sentences. And in logic, you would do them as universal quantifiers. And if you look at the examples in your textbooks of universal sentences, almost all of them are generics. All men are mortal, to take the classic example from Aristotle. While these universal sentences, they're about facts. And if I say all people in this room understand English, it's a matter of fact, it's not a generic. We need to distinguish these two types of universals. And in logic, this is very seldomly done. And this fact that all people in this room speak English is part of what I call the fast process. If somebody comes in that doesn't speak English, this sentence will very quickly turn out to be false. While all men are mortal is then a part of the meaning of being human, more or less. It's a very central part. Okay, that's more or less a parenthesis about the generic sentences. I define the object categories, a set of relevant domains. They may expand it over time, as I showed you with Apple. And there is a set of convex regions in these domains. Sometimes it's all the entire domain. There is a salience weight of the domains. Some domains may be different, of different importance here. What is the difference between the meaning of roe and caviar? They note exactly the same kind of things, the same objects in the world. The only difference is that when you talk about something being roe, it's the biological property, it's the eggs of the fish. While you speak about it as caviar, it's exactly the same. It's an item of food. So roe, in the roe case, you focus on the biological domain, so to speak. While in the caviar case, you focus on it in the food domain. It's something that's edible. But it's exactly the same thing. Another example that I have from Lanaker is, what is the difference between beach and shore? Well, beach is if you come from the land side, and shore if you come from the seaside. It's the same thing, but it's depending on what you're doing here. It's not, that case is not so much a weight of the domain. But I mean, sometimes we mark it differently here. And then, of course, there is information about how the regions in different domains are correlated. When I do this, I always do a very simple example with the audience. Please show me the size of a spoon with your fingers. Show me the size of a spoon. Okay, thank you. You're fairly well. Now, show me the size of a wooden spoon. Thank you. It's bigger. You have a very precise notion of what is the prototype of a spoon. It's about 20 centimeters. A wooden spoon is about at least 30 centimeters. So we have these correlations in our heads. Yeah, I mean, I asked you what the size of a spoon, and you picked out the prototype. The spoon picks you to the prototype of a spoon, and that's a metal spoon. Once I add a wooden spoon, you change the prototype, and the correlation is different. We have a lot of information in our heads about these correlations. Another classic example is that you come to an island, somewhere, well, you've lost your way, you end up on an island, and you meet one person there. It's a man, his skin color is brown, and he's fat, he's obese. So, what is the probability the next person you meet on the island is a man? Come on. What is the probability the next person you meet on the island? 50%, yes. What is the probability that the next person you meet on the island is brown, has brown skin color? 90%, very high. What is the probability the next person is fat? You don't know. I mean, we all give these answers. I mean, some correlations we have very precise figures for, some we don't know. So we have a lot of information about correlations between domains in our understanding of the concepts. And that's part of the meanings. And that's part of our prejudice, by the way, anyway, so it's another story. And part-whole relations, that's a long story, but I don't really want to get into that. If you want to ask me afterwards, I can say something about part-whole relations. That's actually quite important, but let me skip it for the time being. Here is Alan's example that we mentioned earlier. That changing the salience of domain can change the categorization. So here you have a space where you have three prototypes. This is the prototypical fish, this is the prototypical bird, and that's the prototypical mammal. And the Q is the whale. And if you put relative importance, this dimension are the ecological variables, how they live and so on, what they do. And these are the biological domain. If you put relative importance on the ecological side of the whale, it's categorized among the fish. But if you expand the biological, you put more emphasis on the fact that it has lungs and it has warm body temperature and so on, then it will be classified as a fish. The relative distance between these three properties is the same. I mean, the locations in the space are the same. But as you see, as you stretch one domain here, you will reclassify the whales with the mammals. And I think that's what happened. I mean, we put more emphasis on a little bit more on the biological sides. The biologists tell us that whales are mammals. So, and they have reasons. I mean, it's warm-blooded and it has lungs and so on. And that changes it from the earlier, more ecologically oriented classification. And this kind of definition or changes we find in natural languages as well, depending on what becomes more salient in our communication about the things. Okay, that was a side remark. So, an object, for me, is a point in a space, is a degenerate region. This is a kind of Leibnizian definition that an object is defined by the set of all its properties. And in my terminology, it becomes a point in a space. But that means that once you have located it in a point in a space, you have given it a value on all of its domains. You've given it a color, a size, a weight, and so on, depending on what domains are in your space. And these, since, say, colors, the different colors are not overlapping. Green is not overlapping with orange or with red and so on. These points will always have a consistent set of properties. It will never be red and green at the same time, because it's located at one place. It will never be big and small at the same time, and so on. So you don't need to have, once you have the structure of the domains, you don't need to add meaning postulates. And I'll get back to that point when I talk about the semantic web at the end. So describing an object is just giving it values in all dimensions. You can have partial description of an object. You don't have to give it a value for all domains, but the partial description may still be sufficient to determine its category if you have picked the most salient dimensions. And another thing about this approach is that there are lots of points in the space that have no correspondence in reality. I mean, you can have, I have no good example here, a unicorn. They don't exist. But you can form, construct a unicorn as a kind of deer with one horn in its forehead. It's a possible object. It's something that you can fit into a great conceptual space and so on. So fictional objects is no problem here because they are just possible points in a conceptual space. So they are treated in the same way as ordinary objects. It's a simple model of fictionality. Okay. Sometimes we make a distinction between physical objects and abstract objects. And the distinction I make here is simply that physical objects have first of all, they have a location in space and time. But an ordinary assumption we make, this is an assumption from our cognitive system, is that an object is spatio-temporally continuous. If one object is here, and then a tenth of a second it's over there, it's not the same object. I mean, unless you see the trajectory of the object moving from one place to another. This is what Piaget calls object permanence. It's a part of our cognitive system that we assume that what we identify as objects are spatially, temporally continuous. They move without jumps in space. So to define a physical object, I could add this assumption of an object has a spatio-temporal continuous path. It's a bit, okay, I forgot to say that I'm talking about this in fairly informal terms, but I'm all the time having in the back of my mind that this should be implementable in some kind of computer system. And this idea of a spatio-temporal continuous path is a little bit tricky, but maybe it can be done.
I don't think you can deal with fictionality just by saying it's a possible object within an agreed conceptual space. I think sometimes the fictional object only appears within a conceptual space which you may reject, which you may think is also fictional. So I was thinking about ghosts and zombies, you know, so if you think a ghost is a spirit, a soul without a body, and a zombie is a body without a soul. I mean, I've got to accept dualism to understand that those are possible. So I don't accept dualism, but I can understand dualism enough to have a conceptual space in which I can place those things.
Thank you. Very good comment. No protest. I mean, I totally agree here. Yeah, and also fictionality has to. I mean, if you talk about fictional things also have to apply most of the time to spatio-temporal continuous things, unless you're writing science fiction and you do this kind of body transports. What are they called? These transports over long distances of space within an instance of a second. Teleporting. Thank you. Teleporting violates this principle. Yeah. Yeah. Okay. Yeah. They are hard to understand, exactly. I mean, I'm talking about children learning their first languages. This is my primary goal. Okay. So, objects as categories. The communicative function of a noun is to identify reference. I mean, I'm talking, give me the chair. I mean, this is what we use them for. This is the... I didn't talk about the function, but that's what they are. Nouns refer to concepts. Names refer to objects. So we have names. Now you can ask why, when I talk, I mean, give me the chair. You don't know exactly what chair I'm asking for. Why don't I have a name? I call that Alice and that Beatrice and that Camilla and so on. I give the name to each chair here, and then I say, give me Alice. Why don't we do that? Well, reason is, of course, cognitive economy. If I were to remember the name of each individual chair here, I mean, my brain would be cluttered immediately, and I couldn't do it. We need to simplify things. And of course, when we learn language, we have the word apple up here, and we group things according to that. When you become an expert, you don't only talk about apples, but you talk about Cox Orange and Granny Smith, and I don't know what the different kinds are. You go on to subcategories. The more of an expert you are, the more nouns you need in order to solve your practical problems. Or if you're a carpenter, I mean, you don't only talk about hammers, but you talk about different kinds of hammers and whatnot. So depending on your need, you will have different levels of specificity in the nouns you use. And in prototype theory, Eleanor Roche talks about the basic category that covers what she thinks is the most cognitively economical classification of the world. But this basic category can, of course, vary depending on your degree of specialization. Now, I guess the basic idea here is that nouns refer to concepts, names to special concepts, that is, degenerate concepts, points in a space. Now we get to adjectives. And they have two communicative functions, actually. One is to help in identifying a book. I mean, I say, give me the chair, and you say, you don't know. I mean, I say, the yellow chair. I mean, because I'm pointing a bit vague here. So if I try to communicate identifying a referent for cooperation, a noun may not be sufficient. There may be many things falling under the noun. I need some property that distinguishes it. I can talk about the tall chair, or about the blue chair, or the far chair. Lots of properties we can add. That's one function of adjectives, to help specifying an object. And the other one is the predicative use of adjectives, where we say that the stove is hot, or the book is red, and so on. We say something about an object. We inform about the properties of an object. In English, in the European languages, the same word class is used for both these functions. But there are actually languages that have two word classes, one for the referential use and one for the predicative use. So it's not obvious that you have to classify these two functions into one word class. They can be separated. But anyway, they have a lot of properties in common. And now I'm putting forward an empirical proposition here, empirical thesis. And it's quite strong, and I invite you to find counterexamples to it. And there are probably counterexamples. So my idea is that the meaning of an adjective can be described as a convex region in a single domain. Convex region, single domain. This idea will come back for several word classes. I'm using my notions of convexity and domain here. So let's try this idea. No adjective means green or orange, because that's not a convex region. No adjective means long and hot, because that's there are different domains. So this is an empirical claim. It's a very strong empirical claim. I don't even believe it's true, but it's true enough that we somehow pick up this, that if something functions as an adjective in our language, we know that it only refers to one domain, and then we have to figure out whether it's the color domain and the size domain, when we're learning the language as a child. And we also know that things that fall under this adjective are similar enough that they form a convex region. So this principle is extremely important in language learning. It will simplify how we pick up the meaning of words. Yeah.
I have a question. I don't have a thing in the microphone.
Yeah, okay. This is part of the procedure.
Well, okay. So we are treating adjectives as those having only one region. What about relational adjectives, which refer to something that is a noun and that probably spans over several regions?
Yeah. Oh. Sure.
You don't really have that much. Or in French, it's rather rare. But if you take Slavic languages, for example, or German, you often have adjectives which are clearly distinct from nouns in predicative function, which are, their only function is relational. I know, what would be a good example? Okay, let's take Polish or Czech for that part. You have dom, which is house, but if you say that you have house appliances, this house here would be domowy, which is clearly distinct. And those languages, Slavic languages, some Germanic, I think, as well, and many others, we just have to distinguish between those concepts.
I can answer part of it a bit later when I talk about functional properties. But there are other relational properties that are a bit more difficult to me, and I haven't prepared them, so I can't give you a full answer. I'll give you a partial answer in a few minutes, I think. So, I mentioned earlier that there was good evidence for this criterion, and this is Gerhard Jäger, who investigated. There is this World Color Survey, and there is data from 110 languages. For some of the languages, there are only a couple of informants. But they have gone through all these Mansell color chips, and they have given their language name for these chips. And the color space, you've seen the topology of that. And Jäger did a study of all this data, and he found that 94% of the data could be explained by convex partitioning of this color space. And 94 is not 100, but the main deviations were for the very small languages. We had two informants, so there is a bit of statistical variation here. Of course, people don't agree perfectly on where the borders between the colors are. But in general, this is very strong evidence for the fact that all languages, I mean, this is all the 110 where you have data, all color terms correspond to convex region of the color space. So convexity got support. I mean, I don't have corresponding data for many other domains, but this was very promising. Now, let's say it's some potential counterexamples. Your example is not among this. I mean, ripe seems to be a product between red and sweet. I mean, you change the color when you look. So it's both the color and the sweetness. And what happens here, I should maybe draw on the blackboard, is that you have a two-dimensional space, you have ripeness, and you have sweetness. The point is that ripeness and sweetness are correlated. So if you look at berries, you get some kind of correlation here. And what happens is that you can introduce a new dimension. You can have a derived dimension, and this would be, this is redness. This is red and this is sweet. And so ripe would be this line that is the correlation between red and sweet. It's a bit of a counterexample, but you can still talk about, because of the correlation exists between red and sweet in berries, then you can talk about ripeness. It's a bit of a counterexample. Yeah, that's what I talked about. Healthy is another example. What is healthy? Well, that's actually not being sick in any of the possible sick dimensions. That's what healthy means. And what you could do here is to take the product space of all the health domains. And then healthy means the corner close to the zero in all these dimensions. That's what healthy is. And it still turns out to be a convex region, hopefully. I mean, how the health space looks like, I don't know, but there are a number of dimensions, I mean, as I mentioned here. Yeah, I mean, none of these examples are perfect, but anyway. So, is a convex region I should have written in a multidimensional illness domain. Here is a kind of interesting example. Kinship classification. I've taken that example because to show you that this comes from the Dutch linguist Joost Swartz, that here you have a product space. You have two dimensions. One is the dimensions of generations going down. You have you, your children, your grandchildren, and so on. And by the way, this is only done for the female part of it. And then you have generations before you, your mother, your grandmother, and so on. Joost Swartz's idea is to look at these two dimensions as a product space. And then you see that this is English. And you get cousin here. And in English, you don't distinguish between first cousins and second cousins, you call them. Many other languages make distinctions between the number of generations that are between you. In English, you don't. Where is aunt? Yeah, you have aunt, sister, aunt and grandaunt and so on. I mean, it's all aunt after a while, I mean, number of generations. Some languages have one term for this part. Sister and aunt has the same term. That's kind of common. And some languages have same term and so on. Joost has done a survey of different languages. I mean, there isn't very much of convexity, but there's still some convexity. Cousin is a convex region of this space, and aunt is actually a convex region also. And he looked at the number of languages, and he found that with this representation of the product space, the kinship terminology is convex. It's a discrete space, but you can still talk about betweenness in terms of generations. So, I mean, it's a bit surprising, but it's a way of representing the information that makes it convex. Okay. Here's a quote from Linda Smith that talking about how kids develop their understanding of the world. She says that there is dimensionalization. That means at the beginning there is a buzzing, blooming confusion, as William James calls it, that we confuse all domains in one big domain. And then we learn to separate out the different domains. We learn to separate out color, we learn to separate out size and shape and so on. And actually there is a particular order. We learn shape very early and color a bit later and so on. So the first are the basic categories. Well organized by overall similarity. There is correlation between a large number of domains. They're not, superordinate is a different thing. We refer to dimensional relations, read or tall, understood relatively late. So it's easier to learn the meaning of a noun, because that's a correlation of a number of domains, and we are very good at picking up these correlations. Then understanding the meaning of an adjective means that you must have separated out a particular domain to see that we can talk about colors, to see that we can talk about temperatures and so on, and see that we can talk about money, I mean, in terms of mortgage and inflation, as I mentioned earlier. That's something that some of these domains come later. And actually, if you look at child data, nouns are much more frequent than adjectives at early ages. Kids learn more nouns than they learn adjectives. And later on, they pick up more adjectives. So you can actually look at when certain domains are learned. And I did a bit of a search in the database called Childis, where you have a lot of child speech. So I looked at very concrete things like, this is age and month, and this is frequency in this database. So these are the fruit words. Basically, they are learned about when a kid is about 18 months. The frequency increases here. Sometimes the frequency goes down, but that simply means that they learn more words. I mean, they use it often anyway. And orange is a bit of an odd thing here, because orange can mean either color or the object, and I can't distinguish between them in the database or in this search I made here. Have a look at these words: alive, live, live, die, and dead. I mean, relating to death words here. As you see, they are learnt between 3 and 4. And that's when when children start thinking about, the theory of mind hypothesis. This life and death comes when they're about 3. The understanding of and use of these words. There are maybe some earlier examples. But the point here, my point here, is that these words, they belong to the same domain. They are learned at the same period. So this domain comes late. Knowledge domain comes also between 3 and 4 in general. So there are two, actually, domain spurts in the development of a child. One is when they're about between 1.5 and 2. Then they learn about all the basic domains. And you can show that by looking at this. And then somewhere between 3 and 4, there is a spurt when they learn about more abstract domains, like life and death and all the theory of mind things, like knowledge and so on. So you can see when a certain domain is picked up by a child by looking at data in this case. So that was well, not only adjectives, but still some other things. Okay. Now I've talked about nouns and adjectives. Now I want to get into verbs. And verbs has not been treated very extensively in cognitive linguistics. And my way of doing this is to giving you a theory of actions and events. So let's get into actions. Yeah, that's the next part. So I want to talk about action space. And we don't know very much about it. I mean, I said we don't know much about shape space, but we need something. And I've given you this example twice already. What I want to do is to give you some examples from psychological studies of action perception. And this is Gunnar Johansson, who in the early 1950s, he put patch lights on the body parts of a human, dressed up the human in black, and let the person move in a black room, and film the person moving. Then he showed the movies to subjects, and he asked, what are they doing? And they were very quick at picking up this. They needed basically 200 milliseconds to see not only that it's human, but it's a human walking or dancing and so on. So we do this very quickly. And I'll show you a movie if I can get it running here. Let's see now. I need to move my cursor to get down here. So I'll give you 200 milliseconds. And you see immediately that this is a person walking. And I mean, this is not patch light, because this is with reflective tapes, and inverted. But I mean, you see very quickly what's happening here. And even the last one is very kind of easy. Even okay, there's throwing a ball, but this one. That's basketball. I mean, you don't even see the object. You can still infer. The point is that you don't see the surface, you don't see the colors, you don't see the shapes. You only see a few moving dots. And that's enough for your brain to pick out the action. And this psychological data I want to take seriously. We don't need anything except for the movements of the body parts to identify and classify an action. So how do we do it? Well, this is one of Gunnar Johansson's students, Sverker Runesson. He says that the kinematics of a movement contains sufficient information to identify the underlying dynamic force pattern. Runesson is a Gibsonian, and this is part of his Gibsonian ideas. But the important thing is that we don't see the movements. Well, we see the movements, but our minds extract the underlying forces, whether I'm pushing strongly or weakly, or I'm jumping, what forces I do when I jump. So this is my, I'm sorry, my slides may have come in wrong order here. Anyway, now verbs express actions, but there are actually two kinds of verbs. There's what's called manner verbs, and that is how you do something. And then there are result verbs. That is the result of an action. And I will talk quite a lot about this distinction between manner verbs and result verbs. Actions are represented cognitively as force patterns. I mean, when I walk, I have a pattern of moving my legs and my arms, and it's maybe a bit regular. When I throw, it's a pattern of movement of moving my arm. I mean, throwing is different from waving. You saw waving and you saw throwing. We can identify it because it's a different pattern, even if it involves the same basic movements of my arm. The force pattern is different in waving and in throwing. So I don't have a very precise definition of what a force pattern is, but I have some ideas. Talmud talked about force dynamics, but he doesn't talk about all verbs. He only talks about verbs that involves two actors. So it's an agent and a, what is it called, agonist. So it's a bit of a subset of what I'm doing here. But he brought out the importance of the forces in the interaction. He was the first one to write about it. And also in the area of embodied cognition, people talk about the bodies, but it's only about the action of one individual that's involved. It's not quite general enough. So, in general, I want to conclude that the role of forces in semantics has been underrated. And I think that our perception of forces is very important when it comes to verbs. So I want to give you examples of this process. So my idea is that the representation of an action is a pattern of forces. And we can talk about convexity of patterns is here as well. So actions are more or less similar, and I show prototype effects. I had a PhD student who really established that actions have the same kind of prototype. The movie I showed you was from this PhD student who used that in his work. So my definition of an action category is a convex region in the space of force patterns. I haven't really given you the space of force patterns, but this is the general idea. And again, similarity of actions should be investigated to find the structure of action space. You can do this in the same way as you did study similarities of colors in the Mansell chips and so on. So here's one example from, I think it's from one work of Giese and Lappe. So you have one karate movement that you have filmed and another karate movement, and then you can form a morph of these actions, and then you can ask a karate expert if this in-between movement belongs to that category or that category. I don't know enough karate to distinguish these actions, but some people do. So the question is, which is this morphed thing? Is it more similar to action 1 or to action 2 here? On the basis of that, you could find out the borders do some kind of Voronoi tessellation or something in the pattern of forces that are used to generate these actions. We also need these actions to classify functional properties. And now I get back to your question of the relational things here. This is a quote from Paul Auster, City of Glass, and he talks about what is an umbrella. Umbrella is not just a thing, it's a thing that performs a function, expresses the will of a man. And he says that, well, my question is, what happens when the thing no longer performs its function? Is it still a thing, it's become something else? When you rip the cloth of the umbrella, is the umbrella still an umbrella? You can open the spokes, put them over your head, walk into the rain, and you get drenched. Is it possible to call this object an umbrella? In general, people do. And then he says that, to me, this is the serious error, the source of all our troubles. I think that's a bit overstated, but anyway. The question is, what is the defining thing of a chair? Well, I'll get into the case. So, some objects, in particular artifacts, are not defined by their physical properties, like the color, the shape, or the size, but they are defined by their functional properties. So my idea is that they correspond to convex regions in action space. An umbrella is defined by something that you can hold over your head to protect you against, with one hand to protect you against the rain. I mean, that's what an umbrella is. And so here are some pictures of chairs, not the most extreme ones. I don't have beanbag chairs and some other extreme things. So, I'm sorry. Yeah. You can hold them. Yeah, you can hold them over your head. That's a good idea. Maybe not with one hand. It's a bit of an odd umbrella, but yeah. Okay, you can. Yeah. Okay, good. But basically, a chair. I mean, the sitting action. That means you can support yourself, and that's a force relation, and it supports your back. So what is the difference between a chair and a sofa? Well, a sofa has the same things, except that there is more than one person. And a sofa also affords lying down. A chair normally doesn't afford lying down. What's the difference between a chair and a stool? Well, you can sit on a stool, but you can't lean back. There is no support for the... So there is a set of actions. We had a large set of actions. And my proposal here is that the functional properties are defined by the set of actions they afford. And this notion of afford is, again, a Gibsonian idea. Of course, there may be overlap. The actions you can do in a sofa overlaps that of a chair. The actions you can do on a chair overlaps with those of a stool. And there are different kinds of chairs. I mean, ordinary chairs and armchairs. Well, an ordinary chair you can move around and stand on to fix something in the roof. or the ceiling. An armchair is more difficult. You can use a chair as an umbrella if you like, but it's kind of odd umbrella. But still, it would function as an umbrella if you use it. So yeah.
Isn't there a danger that because actions are complex and there are many different ones and there are many kind of different conditions,
yeah,
that you might end up with a huge space of dimensions and nobody's ever explored all the circumstances, especially for complex actions?
Oh yes. I mean, as I said, there are lots of odd things you can do with ordinary things, so to speak. So the borders are vague. But again, we have prototypical actions we do in a chair. We can do odd actions on a chair. But this would be the prototypical regions that would define the objects. I mean, I go by the Of course, there are all kinds of complications that you can add to it.
There's a collection of things which I call polymorphic, but I'm not sure if that's the best word, of which repair is an example. You can repair a chair, you can repair a table, you can repair all kinds of things, but what you're doing will be very different, and that's because of the relationships between the beginning state and the end state and the action. And I think there are a lot of words at that kind of level of abstraction. Efficient is another one, and probably you fit them into your space somewhere, but they don't fit in at the kind of level that you're talking about now.
No, repair is tough, but that's an intentional thing. I mean, it's not functional. The object doesn't fulfill it. The umbrella without its cloth doesn't fulfill it. You can repair it by replacing the cloth and so on. So it fulfills its function. And you're moving the object from outside its functional space, being outside its normal function, into its more normal function. That's a basic meaning of repair.
High level of abstraction,
yeah,
which
yeah.
could be instantiated in many different ways.
Of course, because it depends on the functionality of objects. And yeah, okay.
Okay, just to add to this, and if you can just add an adjective and say, umbrella without the veil is a broken umbrella, and does it still keep the sense? I mean, that's also the use of adjectives to the nouns.
Yeah, broken is interesting because that simply means that you're leaving it has the physical shape of an umbrella, but you're leaving its functional space.
Yeah, well, I mean, it keeps the concept, but it just shows some new feature of the umbrella.
It means that umbrella also has this shape parts to its meaning. That's the prototypical meaning of an umbrella has a particular shape. I mean, the chair is not a prototypical umbrella, even if you can use it. But for a prototypical umbrella, you can say it's broken because it has the right shape, but it doesn't work or whatever. Yeah.
Or maybe just to add an additional dimension. For example, the temporal, the time where the functionality can be afforded. If there is rain, we can use the umbrella, but if there is no rain, it doesn't make too much sense.
No, okay, yeah. Yeah, it's dependent on the context as well. I'll get back to context because context makes things difficult for me, but anyway. Okay, I mean, I haven't developed this in detail, but I'm just showing you that for certain object categories, we do it categorized by the actions rather than by the other properties. So this is one example. Now, the most abstract thing is the notion of an event. And funnily enough, the microphone is... I'm sorry. It's okay, that's fun, that's fun. It has a particular function, I don't know what. Anyway, and it's an event. In philosophy, you find metaphysical analysis, Davidson, Jagon Kim, and so on. They talk about the ontology of events. You can do that, but it doesn't tell you very much linguistically. You have cognitively models of events, and that's what I want to talk about, how you represent events mentally. And then you have linguistic expressions describing events or parts of events. And there is a tradition in formal linguistics that describes events. And I've found that they are often confused here. So very often you'll find in linguistics this kind of definition of the notion break here. So break is analyzed in terms of act and cause. A breaking is that you act in a manner X is the agent here, and Y is the object. X acts in a manner that causes Y to become broken. That's the meaning of break, according to this tradition. It's in the symbolic tradition. So you use acting here and cause and become as a temporal thing. The problem for me is that, what is this? Break doesn't disappear. It's a kind of circular definition. The meaning of break, you don't, I mean, if I had put some arbitrary words here, you wouldn't have learned anything about the meaning of break, except that it's an action that causes something. So this doesn't tell you very much about the meaning of break. But that's a typical way, and that's what I call linguistic expression defining. I want to get out of that symbolic representation and do it in terms of force patterns instead. That's my way of handling actions. So I'm now very boldly proposing a cognitive model of events. It contains two vectors. One vector is the central part is the patient, the thing the event is about. And there is a force vector acting on the patient. Something is happening to the patient. And as a result, the patient changes its properties. Okay, if the event is a state, there is no change, but that's a marginal case. Very often, there is an agent that causes the force, but it's not obligatory. There are cases where there are no agents, as you will see. So this is my basic model. An event is a force vector acting on a patient, giving a result. That's what an event is. So from this model, it comes from force space, changes of the properties of the patient, whether it grows or if it changes temperature and so on. And these results can be changes in location. The patient can move. If I push the chair, it's a change in location. If I paint the chair, it's a change in the color space. So it can be different result spaces. Agent is not always necessary. I mean, events of falling and growing or dying and so on, there is no force outside the patient. It's all within the patient, so to speak. There is no agent. So here's a simple-minded example. Pulling a sled. The force vector is done. This is the agent, that's the patient, and the force vector is this one, I mean the pulling vector, and the result vector is then the movement of the sled up the hill. So that's an event, a very simple example of it. And in general, the force vector is the cause, and the result vector is the event. So this event model, the result vector is the effect. So this event model has implicit a kind of model of causation. Unlike most other models of causation, it makes a difference in the ontology of the cause and the effect. The cause is a force, the effect is a change of properties. And normally people don't make that kind of distinction. Now, there can be more things in an event, and in linguistics these are called thematic roles. So I have the agent represented in agent space that contains at least a force domain. An agent must be able to exert some forces. The patient is an object represented in category space and has a location in most cases. I mean, unless it's an abstract patient. You can have instruments. You can hit something with a hammer. You can have counter forces. If I push, there is friction. So even though I push, it doesn't move. So the force has to be complemented with the counter forces in order to determine the result. And if you have read Talmy's force dynamics, it's very much a question of the balance between the force of the agent and the counter forces by the agonist. So I'm generalizing this in a way here. And you can have the intentions of the agents. I will give you maybe some examples of intentional parts here. Now, this is another very strong statement. A sentence describes an event. That's the meaning of a sentence. I mean, if you look at Frege's definition of what is a sentence describes a proposition. What is a proposition? Well, it's the content of a thought. I haven't read Frege carefully, but basically that's where it stops. So what is the content of a thought? Well, when this has been analyzed in logic, it's been thought of as a mapping between, as I said, between elements of language and words and possible worlds and so on. For me, a sentence describes an event or a state. I mean, I said that a state is a special case of an event, and that is when the object doesn't change its property. I mean, when I say the stove is hot, the stove stays at a particular region of temperature space. Yeah, so a sentence expresses a part of an event involving either, you say, the force vector or the result vector. A sentence doesn't have to specify both. You can say, express one of the parts of the event, and one entity, that is the patient. So that is my analysis of the semantic meaning of a sentence. It represents events.
Does the top sentence on the screen refer to possible?
It's too abstract for me to analyze. But no, it's, yeah, this is probably a state.
That kind of sentence is in another space.
It's another very abstract space. Thank you. And here's an analogy with the visual process. When you see something, you can describe it from a lot of points of view. You have to form a perspective. And when you describe something, you have to choose whether you want to focus on the force part or on the result part of what's happening here. And in linguistics, this is called a construal that you're then expressing. You're not talking about everything you're seeing, but you focus your attention on one part here. So you have an ordinary sentence like Victoria hits Oscar. There the focus is on the agent. While you have Oscar was hit by Victoria, then the focus is on the patient. The passive is, it's the same context, it's the same event, but the difference is where is the focus here. And so there is no in English, there is no simple relation between agent, patient, and subject-object. Subject-object is mainly a question of the focus of your attention, while agent-patient is a question of the roles it has in an event. This is for Indo-European languages. For some languages, I think what is called the ergative languages, it's more the agent-patient that determines the subject-object. But that's something beyond me, basically. But in our languages, subject-object is basically a question of the focus of attention you have in your construal. Now, this is what I had to say about sentences, and that's very quick and rough, and I don't want to spend too much time on it. Let's go say something more about verb meanings here. And again, now I put forward a very strong thesis about verbs. And again, there are possible counterexamples. The meaning of a verb is a convex region of vectors that depends only on a single domain. Now, it could be the force vectors. So push refers to the force vector of an event. And you can push strongly, you can push weakly, but it's an action that is directed away from the agent. Pushing is a force that goes away from the agent. Pulling is an action that goes towards the agent. That's the difference in the meaning. That's the difference in the meaning between push and pull. Push is a force vector going away from the agent. Pulling is a force vector going towards the agent. You can apply that to all kinds of agents. Move, that verb refers to changes in the spatial domain of the result vector. Moving things, you change the location in space. And heat, the verb to heat something, refers to changes in temperature. If you look at basic verbs, again, like the kids learned first, this thesis functions pretty well. I'm not saying it functions perfectly, but again, let me do the meaning of convexity and single domain here. There are no verbs that mean walk and burn, because they're different domains. There are verbs that could mean walk or jog, or walk or run. I mean, some languages don't make fine distinctions. I mean, that's okay, because that could form a convex region. And there are no verbs that mean crawl or run, because that's not convex. But there are verbs that mean run or jog, or run or walk, or things like that. That's possible. So, again, a very strong empirical hypothesis that can be tested in different languages. And I don't worry if it's not 100% correct. I'm happy if it's 90% correct, because then it will still function as a heuristic for a child that's learning a language. Once you hear of a word that is marked syntactically as a verb, you know that it's either about some forces being exerted or by some changes happening in the world. And that will help you in speeding up your language learning. So, predictions from the theory. I can explain similarities of verb meanings. So I can explain why running is similar to walking, while running is not so similar to painting, because the force patterns are different here. Running and yeah, Rob.
Is it working? Is it working? Yeah. So earlier you mentioned adjectives and nouns, and now you said adjectives are coming later than nouns because it involves more domains. Right, so now you say that verbs, they also involve only one domain, so like an adjective. So would you then expect that verbs come later than nouns, and is that the case?
Yeah, in general, I mean, there are some basic verbs that you learn, but in general, they do. And in particular, I think, I mean, I'm a bit uncertain here now, that the results verbs come earlier than the manner verbs. Because understanding forces is more difficult than seeing the results. I don't know enough about the child literature here, but I would say that the first general words that kids learn are mainly nouns, and verbs come later. Of course, there is a parallelism here, but in terms of relative numbers, I would say that the nouns come first. Yeah. Okay. Subcategories of verbs. So, English has a very large number of different subcategories of walking, and I'm only giving you a few examples here. If you analyze them like act to cause something to become, what is the difference between marching and striding and so on? I mean, these are all subcategories of walking, because they are sub-regions of the walking force patterns. And so marching is when you walk with straight legs or whatever marching is and so on. So you can see this subcategorization as represented as subdomains of the walking domain of force patterns. I can actually explain metaphorical uses of verbs in this way. I've only found a couple of examples here. Scything down a football player, that's a quote from a newspaper. So some player was scything, and that means he took his leg and cut the legs of the other one, like you do when you have a scythe and you're cutting down the straw. So it's the same force pattern that is involved in this action. And in tennis, you slice a backhand, and slicing means moving your hand in this way. And that's similar to how you move your hand when you're slicing bread. Not a perfect metaphor, but still. I give it as a challenge to you to analyze metaphors, verb metaphors. And they're more frequent than you think. I mean, once you look at the sports reports, they're full of verb metaphors. And my thesis is that the metaphors work because they are based on the similar force patterns. My favorite example was from a psychological experiment where a small boy was saying that he was vacuuming the milk with his mouth. And that means he was sucking the milk, but he said vacuuming the milk, because the force pattern in his sucking up the milk is similar to when you use a vacuum cleaner. And that's a nice metaphor, I think. The theory predicts the division into manner and result verbs. If you have a force vector and a result vector, manner verbs describe force vectors, result verbs describe result vectors. So that comes for free. And the question is whether linguists accept this. There is a bit of fight in linguistics on whether this distinction holds water or not. That's exactly what I said. So let me give you an example. Here's a manner verb, push. And it's a force applied to an object, this boy pushing the door. And prototypically, the push leads to a change in the position of the object. But as this cartoon from Gary Larson illustrates, sometimes it doesn't. You push, you exert the force, but there is not the expected result. And the change is not certain due to counterforces. I mean, the door doesn't yield here. So there is no change, even if the boy is pushing here. And you can test these expectations with but. I pushed the door, but it didn't open. It means that the prototypical thing means that the door should move here. I can't say I pushed the door, but it opened. That's odd, because that's part of the expectation here. Result verbs. Here's paint. Describes change in an object. So open a door, change an object, grow, move, paint, heat, and so on. Changes an object, different domains. They don't determine the forces that lead to the change. You can paint a house in very many different ways. You can do it with a brush, you can roll it, you can spray it. I mean, there are lots of manners of painting. But the verb paint describes the result, that the object changes its color. That's the meaning of paint. So it's a result verb. Two basic kinds, I already mentioned them, change of position and change of properties. Change of position means that you apply it to the spatial domain, and change of properties are the rest. Here's a funny example. Perception verbs. I hear the owl. What is the difference between I hear the owl and I listen to the owl? Here, you are the patient, and you're passive. The sound comes on you. So that's a result verb. You, as a result of the sound, you hear the owl. But listen is active. You're focusing your attention on the sound of you. You're directing. I mean, this is not an ordinary sense of force, but you're directing your attention, your auditory attention to the owl. You listen to the owl. So that's a manner verb. And in English, you have these pairs. Listen, hear, see, and look. What else? Feel and touch. You don't have it for the taste thing, or for the smell thing. I've forgotten. Yeah, Italian has two different verbs for taste. What is it? Sentire and odor. Yeah, for olfactory. Anybody knows Italian here? Okay. You know what sentire and odora or something like that. Udire. No, this is smell. Udire, thank you. Udire and sentire. So this is the resultant manner verb. In English, you only have smell, which is both. You can actually use it as both. Emotion verbs. I mean, I scare you, I praise you, I blame you, and so on. I exert a force. Now it's a mental force, not a physical force. I'm doing something. But mental forces are included among the forces there. And as a result, your internal state is changing. Maybe your external properties don't change, but your mental state is changing here. So that's also result verbs. Emotional or cognitive spaces. So it doesn't only have to be physical spaces. So that's a little bit of an odd category, but the theory basically applies to this type as well. Now the general question is, why can we divide verbs into manner and result verbs? Some linguists say that there is strong support for it. My idea is that there is a connection between force vector and result vector. That is not direct. There has to be counter forces. So when you're pushing things, I mean, you can feel your forces, but you can't always predict the result. And that means that the mapping from the force vector to the result vector is difficult to learn. I mean, it's dependent on the context, if the door opens or not, and so on. So from a learning point of view, it's easier to learn the separate parts than to learn the full mapping. That's my general take. Here are three different meanings of climb. Climb with your arms and the rocks. Here you're climbing the hill, and this is the air. The aeroplane is climbing. Why can't we say that the aeroplane is climbing? Well, what is climbing? Is it a manner or a result verb? It seems to involve both upward motion, which is a result thing, and clambering, manner. So here we definitely have clambering. Here it's not very much clambering except that the feet is clambering against the wall. Here is no clambering at all, but it's only upward motion. Why can we say climb here? Is it a manner verb or is it a result verb? Well, my analysis is that it is a manner verb because the force vector has an upward direction. That's the basic meaning of climbing here, that there is a force vector that is directed vertically upwards. So Oscar climbed the mountain. You don't know how he is exerting some force up the mountain here. You can say Oscar climbed down the mountain in English. Now you're adding a preposition here to mark that this is not a typical use of climbing. But you're still clambering and you're still exerting an upward force. Even if you're climbing down, the force is directed upwards. Otherwise you would fall. Oscar climbed along the rope. You can climb vertically. The force is still directed upwards. You can say the train climbed the mountain because there is still a force pushing the train up the hill. But the train climbed down the mountain is odd, at least. I don't know about your English, but it is odd. Because if it's climbing down, it's maybe breaking its way down the mountain. I mean, and there is an upward force in its breaking. It's not exerting an upward force in going down the mountain. So you can't do that. And you can have climbing without any arms or something to snake climb up the side of the tank. There is clambering here and an upward force as well. So looking at some different example, my analysis is that it's basically a manner verb. But of course, an upward force typically results in an upward motion. But that's only typically. You can have climbing down a mountain as well. There are differences between languages and how much of these exceptions are allowed. So not all languages accept all these cases. But the prototypical type is still this one. The force vector has an upward direction. You can have different exceptions here from the prototype lexicalized in different languages. State verbs I haven't talked about, but that is when there is no result. Be, sleep, hate, no change involved. There's an identity vector in the property space, a special case of a vector. No force. They're all state verbs are all result verbs, by definition, more or less. Intentional verbs, we get to those. You can exert forces intentionally, and that goes back to these mental forces. And intentional means that you have a desired change in goal space. Here I bring back the idea of us having goal spaces. And when you have an intention, there is something. So, a classical English case, kill versus murder. Killing is causing somebody to die. I mean, you're acting, the result is that person dies. That's not intentional. Can be intentional. Murder is an intentional. It means causing somebody to die. And you have the goal that the person dies, or the animal, or whatever. That's murder. There is a desired change in goal space here. Here is a nice thing I found in the dictionary. What is wink? Yeah, it's a blink. And the intention to awaken the attention or convey private intimation to person. I like that definition of what wink is. But wink is intentional, blink is non-intentional. That's another good example. So, my analysis of this is that an intentional verb actually contains two events. One is a physical event of blinking. I mean, you do something. But at the same time, you're fulfilling a goal. So the fulfillment of goal is a change in goal space, and that is a result. That event, your fulfillment of your goal, is a result. But the physical action is a change in the physical property. That can be either manner or result, depending on the verb. Murder and blink are both changes in physical properties. Yes. So intentional verbs are a little bit odd because they involve two events.
So when you have complex action like longer-term plans, one of the problems that, for example, people when they try to learn these in a data-driven way is that the dependencies are sometimes very temporarily. So for example, you need to pick up a key, and you need to have that key so later you can open a door. How does this work in terms of the goal space? Because certain things may be quite actually different from the current action you're doing? How do they stay encoded in the step that you're doing?
Yeah. I mean, I haven't analyzed sequences of events here because you're talking about the planning sequences, so that would go beyond this model. And I'm noticing that I'm running out of time, so I should speed up a little bit now. I'm basically done with the verbs. Adverbs I don't want to say very much about. I only look at adverbs modifying verb actions, but they are modifying nouns, and you can have direction of vector, magnitude of vector. I don't know whether I want to claim that adverbs apply to only one domain, but they are modifications of vectors, basically. So I don't want to say. Let me say a few words about prepositions because they're more interesting. Again, I want to say that the core meaning of a preposition depends only on a single domain and that they represent convex regions. But the domain of a preposition may be different. Most prepositions refer to the spatial domain. Some linguists claim that all prepositions are spatial. I don't agree. Some depends on the force domain, like on. Some depend on the time domain, like during. Problem here is that prepositions are very often used metaphorically, so it's difficult to find the basic domain. The geometry of the prepositions I describe, now again this is work with Jost Schwarz, so we have written a paper on this. It's described by polar coordinates, so we get a different kind of convexity here. So this path is convex. This is a circular landmark. I'm assuming now that landmarks are circular because that makes convexity easier to define. So let me say something about location of prepositions, inside and outside. So you have a landmark, and inside means this region, and if it's circular, it's polarly convex. If outside means everything outside of the landmark, sorry about the tautology, but anyway, this is, in polar coordinates, this is convex. Near and far. Near means contextually dependent distance from the landmark, and far is everything outside here. Again, both regions are convex in polar coordinates. Front, back, left off, and right off is are all convex in terms of polar coordinates. The preposition between is an exception. I have problems with, or we have problems with between, so that's a possible exception. We have some analysis. Above and below, now we go for the vertical dimension, are still, even though the borders are vague here, when you go up and down, it's still a convex region. Between, you can analyze like this, but you have to decide which one is, what is the landmark here. If you're between, you have two objects, and that makes the thing a bit complicated. So it's a bit tricky. I don't want to get into the detail here. These were locational prepositions. Then you have directional prepositions, like goal prepositions, to and into and so on. Source prepositions, from and out of and so on. Road prepositions, through, over, along, around, across. We analyze them in terms of paths. So the preposition is analyzed as a set of paths. It's a set of paths. And you can define convexity of paths. If you have one path going from A to B and another path going from A to B, you can talk about the path being in between, going from A to B. We do that formally. We define the betweenness of paths. And then it turns out that all these prepositions come out as convex regions of paths, very naturally. So convexity applies very nicely to the directional prepositions. Some prepositions depend on forces, like being in. This pair is in the bowl. This pair is same spatial location. It's not in the bowl. The difference is that there is a kind of physical force relation here. Is this lamp on the balloon? I'm sorry, the balloon should be touching the lamp here, but anyway. Would you say that the lamp is on the balloon? No, you wouldn't. Even if there is physical contact. And no, the reason is that the balloon is pushed. Normally, when you have put something on a table, there is the physical forces going downwards. Here, the balloon is coming and pushing upwards. So on is dependent on. It's not a spatial relation. It's the force relations that determines on. I don't want. Here is over. This is Garrod and some other people asking people whether this umbrella is over the head, and people say yes. Here they say maybe, and here they say no. But then you add rain, a slanting rain here. And then people say yes, and then they say yes, and they say maybe here. So the rain, direction of the rain, the force direction here, changes the perception of what is over. It's not a spatial relation, but it's the relation in terms of the forces of the rain that determines whether it's over or not. Demonstratives, well, I don't want to spend this, that, here, and there. They are simple word clause. This and that refer to category space. And again, that's their distinction is in whether the distance. This is here, that is over there. Here and there refer to physical space. Yeah, I don't want to spend time on that. And I wanted to say something on quantifiers, but I skipped that because it's a bit complicated. So I have an analysis of quantifiers. Let me summarize this cognitive grounding of categories. I've talked about object concepts representing by noun properties, adjectives, domain relations, prepositions, not only spatial domain relations, force and result vectors, verbs, modifying vectors, I didn't mention, present intenses, and yeah, demonstratives, events expressed by sentences. Object concepts are an exception. Sentences is not a word clause. For all of these word clauses, I would put forward this thesis of they refer to a single domain and they refer to convex regions within these domains. So this is a very strong claim about how our word clauses work. I mean, with the exception of nouns. This is a cognitive claim. There might be counterexamples, but if they are 90% right, then these will help kids in learning to what are the meanings of words. These are constraints that will speed up language learning quite efficiently. I'm afraid I would like to skip compositionality meaning because I want to say something about the, let me do it, I could, sorry. Okay, metaphor. It's not composition. So, what is metaphor? What is the meaning of bumpy? Well, that's a spatial predicate. You have two dimensions, or you have three dimensions, two length dimensions, and two horizontal dimensions, one vertical. And bumpy means having some kind of irregular form here. Now you can talk about the bumpy relationship. And then what happens is that you have the problem level in your relationship, and you have the time dimension, and you can make this. So it's the same shape. This is only a single example of how metaphors are analyzed. But what happens is that you take well-known physical domains, more basic domains, and you apply them to more abstract domains like problem level. But the structure of the meaning is basically the same when you transfer between domains. Okay, this is my summary. I don't want to read it, but this is what I've done here. So I want to get to the applications. Symbolic methods. Traditional computation involves rule following based on recursive procedure and tree-like structures and search algorithm, basically. That's what computation is at large when you do analysis here. What I do instead is vectorial representations. You have matrix multiplications, you're changing scales, you're changing what? Coordinate transformations. You take inner product spaces, you look at the Voronoi tessellations, representations of similarity. Totally different from a computational point of view. The question is whether you can marry these, and maybe you can. I have a criticism of the semantic web, and I claim it's not semantic, it's ontological, and now people talk about the ontological web. Basically, it's taxonomy plus inference rules. Berners-Lee, who introduced this, he says that fortunately a large majority we want to express is along the lines of a hex head bolt is a type of machine bolt. Well, my argument is that this is not true. I mean, he's giving an example of generics, and he says the generic is what we need to formalize. It's not. What's missing here is the role of similarity, and you don't get similarity in this kind of criticism. Yeah, you only have expressivity of first-order logic, sets of objects, they are not grounded outside the system. That's another criticism of the symbolic system. I should have spent more time on this, I'm sorry. However, some people have tried to extend, this is a paper by no, I'm sorry, this is not what I'm saying. Okay, if you instead look at conceptual spaces as a basis instead of a symbolic, the conceptual hierarchies, the taxonomies that I have, will emerge from inclusion structures of the concepts. I mean, I gave you one level of Voronoi tessellations, but you can have subordinate and superordinate tessellations. So that kind of conceptual hierarchies is built into the Voronoi tessellations. Identities of concepts correspond to identities of regions. You don't have to specify that. Once you have the region specified, you know the identities of concepts. Identities of names, given by identities of points. When vectors are incomplete, you have a bit of a problem. Property characteristics like transitivity and symmetry are implicit. I mean, if A is longer than B and B is longer than C, then by representing them as points on the line, you immediately have that A is longer than C. So transitivity follows from the geometrical structure, or the topological structure here. Yeah, you don't need the additional rows. I should have spent more time on this, I'm sorry. Some people, Adams and Robel, wrote a paper where they presented conceptual space markup languages. They want to marry my theory with the traditional HTML language. So they have proposed a system that looks a bit like this. You want to specify the meaning of tall. And you say that the domain is in the size domain. And then there are classifications here. You have to depend on the contrast class that I didn't talk about. I don't want to go through the details here. But what I do is that they specify the domains and the domain structure and the conditions for the meaning of a word. Tall means that an object belongs to the upper half in the terms of the size domain in relation to the contrast class you're talking about. So a tall squirrel would be different from a tall elephant in terms of sizes, but in terms of the relative sizes, it would still work. Well, yeah. Now, I'm involved in a European project on implementing some of these ideas, in particular the manner and result distinction in verbs with a robotics project. So I think I'll finish instead of saying you that you can have different ways of saying things depending on the focus of attention. You can formulate different things here. But the interesting thing is that choice of verb can focus on action or result. So we've actually implemented this in a system. So let me finish by showing you this movie, if I can find it. Let's see, where's the cursor? There. And I want to move this too. Here we go. So this.
I want you to understand language.
I'm ready. Tell me a sentence.
Before you push the cursor on the right, point to the cube.
I have understood. Before you push the cursor on the right, point to you. Is it okay?
It's right.
Point to you, push cursor right. I will do the actions. Questions?
Yes. What did you do?
I pointed the cube.
And then? What happened?
The cursor moved on the right.
How did that happen?
The cursor has been pushed by me on the right.
What did you do?
I pushed the cursor on the right.
And then?
I have no more information. Tell me another sentence.
Stop the interaction.
So this is the state of the art of interacting with the icon. We are trying to implement different linguistic expressions. I mean, the object relations left off, right off, and so on. That's prepositional. But we're adding this manner result verb that's the latest edition. Next step will involve pronouns. Hopefully, I mean, we will meet later this week to discuss the next step, but pronoun is my hope here, to keep track of, to build up a kind of common ground on this. So we are actually implementing these concepts of verbal semantics in the icon. That's part of the project. Thank you very much, Lisboa. I'm sorry for the
So I think that was fascinating as far as I'm concerned. I've learned a lot of things, and I think it was a very broad overview of a lot of deep questions and very deep ideas about how these questions might be answered. I'm sure everybody's keen to have lunch, but I believe, if there's one or two questions.
I'll be around during lunch.
Oh, and also there's lunch, of course.
Yeah, okay, we can have a couple of questions if you allow it. I mean, okay.
It's great stuff. I have a doubt about some of the basics, but I suspect they can be repaired. You're assuming something about the kind of metric space that comes through sensing and perception and so on. And I don't believe biological sensors produce that kind of metrical structure. It's more a collection of partial orderings and topological relationships. And that would slightly alter the mathematical details, but I suspect you could keep quite a lot. But for instance, Voronoi tessellation assumes a pretty rich metric, and you could make it more sloppy and looser and so on, and still keep the main idea in what you're doing.
I totally agree. I mean, for many domains, we don't have the metric structure. We have between us, we still have convexity. I would claim that. On the other hand, when you're doing robotics like this, it's very nice to have a metric. You're assuming that things are metric, and then it's much easier to implement.
Criticisms of a lot of work in robotics, they're imposing the structure, hindering a lot of intelligence as a result.
On the other hand, I've pointed you to areas like color spaces and the prepositions where you want to have polar coordinates instead of standard Euclidean ones. So I'm giving you a little bit of how you have to twist the mathematics in order to have a more natural approach to language.
Well, I come from the philosophy corner, and I'm trying to figure out what you mean with this idea that meanings are in the head. So you were saying that if you talk about concepts would be working in different domain regions, no? I guess we should put concepts on the one side, because you were saying that verbs, adjectives, and prepositions operate in just one region, no? So like you are separated on the one side concepts, on the other side adjectives, verbs, and prepositions would be put aside from concepts somehow. No, well, that might be terminological issues, it doesn't matter. But if I figure out something like an apple, for example, the concept of an apple, how am I to imagine what I have in my head? Do I have something like, you said it's something like a set of convex regions, no? So do I imagine something like different formats, different metrics that I have in my head, and when I see an apple there, I apply like different transparencies, and then different points converge there, or how am I supposed, or do I have something like a converge, something like an stereotype or something that I compare the apple to, or how is this idea supposed to?
You may be sitting at the telephone describing this fancy apple you saw. I'm sitting at the other end of the telephone, and I hear you use the word apple. My mind, I mean, this is the fixed point idea. I will first of all form a prototype of an apple. You start talking about the apple. I will think of a typical apple. Then you say that...
Is it an image I'm getting?
I'm not... Well, we can talk about to what extent this is image-oriented, I mean visually-oriented. People in cognitive linguistics talk about image schemas. But I would say that apart from the visual part, it's also the force relations that are involved. It's not only vision. So there is more to it. But when you use the word apple, I think of a prototypical apple. Then you may say something else that may have may lead me to move away from the prototypical apple. You may say that this is a new kind that is a blue, and I have to form this odd idea of a blue apple, and we move around it like that. But my point in this fixed point idea is that when you say a word, I'm initially assuming that it means the prototypical meaning of the word, and then further information may lead me away from the prototype to other parts of the apple region.
Just my problem was if I'm alone, okay, now, and I see the apple, no? Do I compare something to something I have in my head somehow, whatever it is, or do I put some structure into the object and say, okay, it matches my structure somehow?
You don't have to do anything unless you start communicating about it. You may not see it as the object. You may see it as an apple, but you may see it as a cox orange or as a fruit or something to play with your child or something else. I mean, you may categorize this object depending on the context. So it's not necessary that you categorize it as an apple. But when you communicate, you have to choose some of these finite number of words to say to me, and I have to understand what you're saying.
Okay, think about it.
There are no more questions.
Maybe just one more question, quite similar to the previous one, but please forgive me my insistence, because you have presented us some very typical adjectives which you consider being very simple. You have also shown us a counterexample of being healthy, that is just being defined by not being ill. It's easier to define who is ill. But then you have the same problem with a number of adjectives. For instance, long or old, because if you say someone is old, it means, well, they have some big number of years they have lived through, but if you ask, how old are you? You're not really imposing that, or something is long, or 5 meters or feet long. Here is the difference.
Now, this is the part I skipped about compositions of meanings. These meanings like tall and short and high and low, and I mean all these comparative adjectives, they're depending on an implicit contrast clause. So if I talk about the tall squirrel, I will have a different meaning than of tall than when I talk about a tall animal. A tall squirrel is not a tall animal, because the contrast clause of squirrels is fairly small, and while the animals is much larger. So tall means within the contrast clause above average height.
Yes, but would you then consider... Okay, that I understand, but would you consider any of those dominant? Because you can say that something has a length of 5 feet, but you cannot say it has a shortness of 5 feet.
I see, you're talking about this positive and negative polarity of adjectives.
Yeah.
I have no general rule. I mean, for some adjectives you have positive and negative, and in general polarity. And in general it corresponds to the directed dimensions. So you have a positive direction of the dimension, and the positive part of the direction is given positive polarity. For some dimensions you don't have any directionality, then you don't have any polarity either. So not all adjectives have this polarity property that you're talking about. There is a general pattern. I haven't really studied it, but I think we can answer most of these polarity questions by looking at the directionality of the underlying dimension.
Okay.
Okay, so let's thank Peter